My name is Brayden McNeill, as I mentioned, and I'm the technical sales and marketing lead here at Aquanty. I can be your primary point of contact at Aquanty for any questions that you might have about HydroGeoSphere, whether it's related to the features or capabilities of HGS, technical support and training. I'm also the primary point of contact for that. If there are any questions that kind of go beyond my capabilities, I have a team of engineers and professional modelers here to help me in the office, but you can reach out to me directly with any questions you might have. So the purpose of the course today is to be a very rapid-fire introduction to working with HydroGeoSphere. The course is going to be mostly focused on the practical aspects of the HydroGeoSphere workflow, but before I get into that, I usually like to provide a bit of an overview of the software itself, its features and capabilities, the design philosophy behind HydroGeoSphere, and sort of the differences between HydroGeoSphere and many of the other modeling platforms that are available on the market. We'll just start quickly with a very quick conversation about the different types of models that are available on the market and the rationale for a fully integrated approach, which tightly couples the groundwater and surface water systems. So in the long history of hydrologic modeling, the vast majority of models have been either focused on the groundwater system or the surface water system. And the impact of the opposite side of the hydrologic coin was basically represented as boundary conditions or forcing data. So surface water or groundwater models, they only represent a single component or portion of that terrestrial hydrologic cycle. There has been a history of different types of integrated models that couple the surface water and groundwater flow systems in different ways. Loosely coupled models are really they're systems where two or more models or modules will be linked together and exchange information, whereas a fully coupled model, such as HydroGeoSphere, truly represents the entire hydrologic model cycle within the context of a single model or a single numerical framework. This is the most comprehensive and physically realistic approach to modeling systems, and really the difference between a loosely coupled model and a fully coupled model is sometimes best illustrated with an example, right? You can take a camera and you can take an old flip phone and you can tape them together and call it a smartphone, but this is really just two distinct pieces of technology that have been connected to each other. Whereas an iPhone or any type of Android phone that we're familiar with these days really is a truly, fully integrated solution that bridges or that combines both the capabilities of a telephone and a camera, right? So this slide just basically shows sort of the landscape of what different types of hydrologic models can do. So up at the top left here, we have surface water models, and at the very far left, we have sort of the simplest representation of surface water flow systems, or lumped HRUs, or hydrologic response units. These are essentially statistical models, and they're not really what I have in mind as I go through my discussion here talking about models. When I talk about a model, what I really am referring to, in my mind at least, is a sort of digital representation of a real-world landscape that is a grid or a mesh-based system of partial differential equations. So there's plenty of examples of this in the surface water world. Xi, 2-flow, J-flow are all examples of that. But really, you have a governing equation of flow, and that governing equation of flow is applied at every grid cell or node within that system of equations. This is primarily sort of the way that groundwater models have worked. There are analytical groundwater models out there, but by far the most common groundwater model in the world is ModFlow, or models based on the ModFlow family of codes. The drawback of ModFlow is that it only handles the fully saturated groundwater flow domain. You can get a little bit more complex, moving a little further to the right here, and there are tons of variably saturated flow models out there. Frac 3DVS is actually the precursor to HydroGeoSphere. Flow is probably the most commonly used variably saturated groundwater flow model in the market. Hydrus would be another example. But as you start to try and bridge the gap between surface and subsurface flow regimes, now you get into the world of coupled models. So as I mentioned before, loosely coupled models really are essentially systems whereby different models that are focused on a single set of governing equations that look at a particular portion of the hydrologic cycle, you'll have multiple of these sort of modules linked together. Mike Shi is a good example of this. Mike Shi handles one-dimensional surface water, two-dimensional surface water flow. It handles three-dimensional fully saturated groundwater flow. And the unsaturated zone is represented typically using a one-dimensional hydrologic routing mechanism. And then we have, HydroGeoSphere, an example of a tightly coupled model that really bridges the gap and brings all these different zones or these different governing equations of flow into a single unified numerical system. And what I really mean by that is kind of highlighted in these next two slides. When you have a model that's based on a system of partial differential equations, you'll end up with hundreds or thousands of equations distributed across hundreds or thousands of grid cells or nodes throughout the model domain. That system of equations is then solved using linear algebra, and you'll end up with a matrix of equations that looks something like this, simplified, highly simplified, of course. On the left side of the equation here, we'll have a matrix of coefficients, this A matrix here, which basically is the product of all nodal properties in the model. So you'll have a diagonal term here, or a series of diagonal values within this matrix that represent nodal properties. You'll then have a vector H, which contains the unknowns that are being solved for in the system of equations, typically hydraulic heads. And on the right side of the equation, you'll have a Q vector, which represents the impact of boundary conditions or mathematical forcing functions. So things like prescribed fluxes or prescribed changes in storage. And this matrix of equations will be solved iteratively. Now, the difference between a loosely coupled model and a tightly coupled model is kind of illustrated here. With a loosely coupled model, you have separate matrices of equations constructed, for different regions of the model. So you'll have one matrix of for subsurface flow, for example, and another for surface flow. Now, these different systems of equations will have some nodes that are common amongst them, right? If you superimpose a surface water flow model on top of a three-dimensional subsurface mesh, you'll have these shared nodes, right? So those are represented here as the red dots within your head vector. The way a loosely coupled system works is that you'll solve one of these systems of equations first, and then the resulting value of heads from shared nodes would be mapped onto the opposite model, and it goes then through a series of iterations to solve itself, and the resulting head values are then mapped back up onto the surface model, and then back and forth, and so you end up having this multi-layered iterative approach. First, the surface water model has to iterate potentially dozens or hundreds of times, solved, pass information down, iterate, and then back up, and so the whole thing just becomes two levels of iterations. So it's not extremely numerically sophisticated. With a tightly coupled model such as HydroGeoSphere, we're really just building all of our different governing equations of flow into a single matrix. You'll have within your matrix of coefficients here, then you'll have different regions that are associated with different governing equations of flow. So you would have all of these nodal properties. Here we have PM, that stands for porous medium. Here we have OLF, that stands for overland flow. Here we have ET for evapotranspiration. So all of your nodal properties will lie along the diagonal of your matrix. You'll have these off-diagonal terms here, which I've kind of indicated as X. And these are basically, they facilitate the exchange of water between nodes that are shared between different model domains. In the world of HydroGeoSphere and over the next couple of hours, as I use the word domain, what I really mean are simply groupings of nodes that all share the same system of equations. So I may reference the surface or overland flow domain, which would basically be all of the nodes on the surface of the model. I might reference the subsurface or the porous medium domain. That simply means all of the nodes that represent the subsurface flow system, the governing equation of which would be Richard's equation. So the reason that we've decided to take a tightly coupled approach with HydroGeoSphere is that having a single system of equations that can be iteratively solved basically introduces fewer failure points. Loosely coupled models can be very difficult it can be really hard for them to actually converge on a solution. So with a tightly coupled model, if you have less difficulty actually converging on a solution, you have a higher likelihood of a successful project. As well, these tightly coupled models, if well constructed, should generally be faster than solving a loosely coupled system of equations. So this is what HydroGeoSphere is really all about. Now, why would we even want to take an integrated approach to hydrology? Well, surface water models and groundwater models, as I mentioned before, they have to represent the opposite side of the hydrologic coin as boundary conditions, right? So a surface water model will have a prescribed base flow value typically. But when you apply a mathematical forcing function to your model, whether it's a groundwater model or a surface water model, you don't really have the ability to represent those forcing data dynamically. You may have changing base flow over time, but the value of base flow that changes over time is simply prescribed by you, and it's not really informed by the overall hydrologic system, at least in a numerical sense, as you reproduce it in the context of a numerical model. Now, you can couple surface and subsurface models weakly through simple iteration and feedback, but that requires you to run many iterations of your models in order to understand how changes to the surface water flow system, for example, may impact groundwater recharge rates. And that allows you to update your groundwater model, and you can run it again and understand a little bit better about how groundwater exfiltration may impact the surface system, but then you end up going back and forth. With a fully integrated groundwater surface water model like HydroGeoSphere, the dynamic exchange of water between the surface and subsurface happens automatically and just as a regular course of practice with these models. So they really allow the hydrologic system to be extremely dynamic and kind of respond in a physics-based manner to to actual meteorological or climatological forcing functions. So with a fully integrated model like HydroGeoSphere, we'll typically handle all of the processes that you see listed on the right in this image on the right-hand side of the screen. They're handled internally by HydroGeoSphere. They become part of the solution to your model rather than being a prescribed mathematical forcing function. The one exception, of course, is precipitation, which the great thing about a fully integrated model is that the primary forcing function, which is precipitation, is directly observable and measurable. The data is widely available. And so when you build a fully integrated model like HydroGeoSphere, you simply apply precipitation as your mathematical forcing function or your boundary condition. And the model does the heavy lifting to determine where that water goes once it intersects with the land surface. It will automatically partition itself between overland flow and infiltration and eventually, movement in three dimensions through the unsaturated zone to eventually or potentially, recharge to the saturated groundwater system, or even move laterally and exfiltrate again to the surface flow system. Evapotranspiration is also built into HydroGeoSphere and is dynamically determined based on available water in the near surface zone. But yeah, basically that's the beauty of a fully integrated approach, is that it does really simplify the conceptualization of boundary conditions oftentimes if you work at the watershed scale especially. So this is what we're all about with HydroGeoSphere. So we attempt to account for all interactions between the surface and subsurface flow regimes dynamically and based on the behavior of the model itself. It's not a prescribed thing. It's not an input to the model. It becomes an output. We simultaneously solve both surface and subsurface flow and transport equations. HydroGeoSphere can also be simplified to consider only individual water cycle components. So while HGS primarily is used by our user base for fully integrated groundwater surface water models, you can in fact treat it as a fully saturated groundwater flow only model. It just depends on how you construct your model, basically. And in every aspect of HydroGeoSphere, we've had a major emphasis on a physics-based approach to representing real-world processes. So a major emphasis on minimizing the use of empirical relationships. This physics-based approach is the most realistic way of representing water movement. It's the most accurate way to simulate hydrologic response of watersheds across the full range of potential climatological conditions that may be experienced in the future. Of course, if you build empirical relationships into your models, by definition, that empirical relationship is based on past data. But as we move forward into an uncertain future, right, these empirical relationships are becoming less and less strong. So it's a great way of simulating watershed response, for example, to climate change impacts and climatological sort of conditions that have never been experienced within a watershed. It's the best way of representing or of testing design topographies. So mine closure designs, flood mitigation measures, all of these, of course, will be difficult to really handle with an empirical approach because those things don't necessarily exist yet in the location of the model. But yeah, the principle of working with an integrated physics-based hydrologic model is to just let the model tell the model what the precipitation and climate characteristics are, and then be kind of hands-off. Let the model tell you where the water goes. This is something that can be a little bit of a paradigm shift for people who come from a surface water or a groundwater only background. Most surface water and groundwater models require a lot of consideration for the boundary conditions and the mathematical forcing functions that are used to define how the flow system works. But ultimately, if you just are allowing physics to do all the heavy lifting and you're working with a fully integrated model, ultimately your forcing function just ends up being precipitation, at which point you should just let the model try and replicate the surface water flow system, for example. In HydroGeoSphere, if you have accurate topography, you don't need to tell the model that there will be a lake at such and such a location. The lake should form as a part of the solution, as should the full network of streams and rivers feeding into and out of that lake. So yeah, this is what HGS is all about. Quickly, I'll just go over some of the key features and the governing equations of flow themselves. So in the surface domain, HydroGeoSphere is solving the 2D diffusive wave approximation of the Saint-Venant equation. In the subsurface, HGS handles a 3D form of Richard's equation for variably saturated groundwater flow. We have a 3D representation of evapotranspiration that's based on I think a 1978 paper by Christensen and Jensen. We handle two-dimensional fracture flow also via Richard's equation, and we can also incorporate a number of different one-dimensional hydraulic features such as channels, tile drains, or wells, and each of these have a few different options for the governing equations of flow that would be applied to them. All of our model domains, i.e. surface flow, groundwater flow, fracture flow, they support generally, temporally, and spatially varying domain properties, so you can actually change porosity or hydraulic conductivity both over space and over time. And we support a dual node formulation for explicit exchange of water between all domains. So this will come up again a little bit later. HydroGeoSphere supports a pretty standard suite of solute transport capabilities. So we have reactive transport, density dependent flow, which can be used for coastal or saltwater intrusion studies, or also potentially geothermal energy transport studies. We have some native winter processes built into HydroGeoSphere, such as a native snow melt and snow accumulation feature, as well as dynamic pore water freezing and thawing. And then HGS has a whole bunch of really advanced numerical methods under the hood. So it is fully implicit, both locally and globally mass conservative. It's a finite element solution by default at its core, but we do also support a finite difference approximation to this finite element system, as well as a control volume finite difference approximation. You can parallelize HGS models locally. It's all based on an adaptive time-stepping system, which we'll talk more about how that works a little bit later on. And we also support particle tracing, dynamic meshing, which allows you to modify mesh topography over time while simultaneously maintaining your water balance. That can be very helpful for mining applications, for example. And more recently, we've introduced the hydraulic mixing cell formulation. This basically treats every nodal control volume in the model as a perfect mixing cell, and allows you to explicitly track the sources of water throughout an entire model. So you can look at any individual node and say, 20% of the water here originated in the groundwater flow system, whereas 80% is from infiltration. And yeah, so a lot of advanced features in HydroGeoSphere. We use HydroGeoSphere exclusively at Aquanty, but we have users all around the world. It's been used at basically every scale you can imagine, from column scales all the way up to, at this point, we're working on continental scale or river, like basin scale models of 2 million square kilometers. Of course, the scale of the model is really going to be dictated by the scale of the problem that you're trying to address or the questions that you're trying to answer. But we have a huge library of research highlights on our blog, and there's no shortage of example applications out there for HydroGeoSphere at every scale. The scale of your model is going to really dictate how refined your model can be, right? So HGS models are based on a three-dimensional finite element mesh. Typically, those mesh elements are triangular prismatic elements, although we do also support 8-node hexahedron block elements. For the vast majority of real-world applications, though, it'll be based on a triangular finite element mesh. The level of spatial refinement is going to be, again, dependent on the overall scale of the model. I usually tell new users to really seriously try to limit your models to a very max of 1 million nodes total. Every node, of course, is a computational point. So if you have 1 million nodes, that means you have, at the very least, 1 million equations in your matrix that need to be solved for, 1 million independent hydraulic head values. The more nodes that you have, the longer your model runtimes will be. And the simple fact is that HydroGeoSphere is based almost entirely on highly nonlinear governing equations. So three-dimensional form of Richard's equation. This is much more complex than Darcy's law. So the model runtimes for HydroGeoSphere are something that all users will kind of struggle with. That's par for the course with a model of this complexity. And so the advice is always to try and bring an austerity mindset into your projects. Really try to work with as few nodes as possible, because that's going to save you a lot of time down the road when you need to run this model a couple dozen times for calibration purposes or to run different case studies. Here we have just a very brief illustration to kind of, it's a very simple cross-sectional model. Has a couple of potholes that water is flowing in from the upper left-hand corner, as well as there's some precipitation. But we can see that these potholes dynamically fill up. This is a small scale, pretty small scale application, but you can consider these potholes, think about them as really large lakes as well if you wanted. But the potholes, they fill up and they overtop dynamically. You can start to see water infiltrating in 3 dimensions through the variably saturated zone. There's a clay layer here at about the mid-elevation of the model. That clay layer ends up causing a couple of perched water tables to appear. And then through that clay lens, we have some randomly seeded fractures throughout, so you start to see preferential flow through those. As I said, it's a pretty simple cross-sectional model, but you would find this type of analysis or simulation to be nearly impossible to do with any other hydrologic modeling platform on the market. This is really, what HydroGeoSphere is all about. The dynamic linkages or dynamic exchange of water from the surface to the subsurface, and a really highly detailed representation of variably saturated flow in the subsurface. And another video here that I'm not sure if it'll actually work. Looks like it's not working, so I've got to update these slides, but no worries, it doesn't really show anything that we haven't already seen from the previous video. Okay, so that's my quick overview of sort of the design philosophy behind HydroGeoSphere and where it fits into the world of hydrologic models. Again, I encourage anyone to just ask questions as they come up. Feel free to raise your hand. Feel free to put some questions into the chat. The rest of the here we go. The rest of this training session is really going to be focused on the practical aspects of using HydroGeoSphere. So HydroGeoSphere, when you install it, by default, there's no graphical user interface. For example, you can't double-click an icon to quote-unquote open HydroGeoSphere the way that I've opened up PowerPoint right now, as an example. HydroGeoSphere is all based on the creation of text-based input files. And these input files are then processed using a number of small applications. And those applications really are what HydroGeoSphere is. So yeah, this whole training session here is really just designed to introduce people to that basic workflow of building the text-based input files, running these executables, and seeing what happens at each stage. Now, with that being said, in 2023 and into 2024, we did actually partner with Aquanty, the developers of GMS. They have, so GMS is a graphical user interface for ModFlow modeling. It typically is used to build ModFlow models. However, we worked with them and they constructed or developed a HydroGeoSphere interface for GMS. So if you're familiar with GMS and you really are interested in using HydroGeoSphere, just know that there is already a way to sort of put the hooks, for the HydroGeoSphere hooks into GMS. You can start to build these basic HydroGeoSphere models in that interface. But for today, we're going to be looking at sort of the traditional workflow based on text file inputs and running the applications directly from the command prompt. Before we really get into that, I'd like to do a quick overview of resources that are available to you. So when you install HydroGeoSphere, by default, it will be installed into the program_files folder on your C drive. Usually it's the only thing you're going to find in there. And on installation, we have a whole bunch of helpful materials for you. First, we have a bunch of documentation. So we have 3 different types of user manuals. I'll open them all up here and give you a brief look at them. The first manual to know about is our theory manual. This theory manual, as you can imagine, provides an overview of the theory of governing equations and the numerical implementation of how HydroGeoSphere works. So there are 2 major chapters. There's a theory chapter. This theory chapter is really focused on the governing equations of flow for the different portions or the different parts of a HydroGeoSphere model, the different model domains. So there's subsections for, porous medium or subsurface flow, fracture flow, surface flow, et cetera, et cetera. As well, you'll find, governing equations relating to solute transport, et cetera. And then in chapter 3, we have a focus on numerical implementation. So here we have a review of the control volume finite element method and the finite difference formulation that are built into HydroGeoSphere, how we discretize all of the governing equations, how they're constructed or put into a matrix of equations, and then numerical techniques here about how we actually solve that matrix of equations. There are obviously a bunch of subsections in here that may not be relevant to your work. For example, if you're not running a solute transport model, you can very easily just skip all of the solute transport subsections. But with that being said, if you're planning on using HydroGeoSphere for research or for, professional consulting project, highly recommend taking a close read of the relevant portions of the manual, so you can understand pretty well what HydroGeoSphere is doing under the hood. Our second manual to note is the verification manual. So in addition to the manuals, our installation folder also includes this verification subfolder. And within this subfolder, you will find 37 additional subfolders, and each one of these subfolders contains 1 or more example problems for you to review and to learn from. These are verification tests that we use every month. When we release a new version of the software, we will run all of these models to ensure that HydroGeoSphere is still producing an accurate solution and that we haven't inadvertently introduced any major bugs that would impact the accuracy of HydroGeoSphere simulations. Given that we want to use these models to verify that HGS is working correctly, we have a large suite of tests that will basically test almost all of the governing equations of flow within HydroGeoSphere. So this verification manual basically contains a description of all of these verification tests. So you can see a table here which lists all of the same folder names that we have here in the verification folder. So if you're interested in building a model that is perhaps it's a heat transfer model, you're interested in the geothermal energy transport capabilities of HydroGeoSphere, you can go to the relevant section, and at the beginning of each section it will tell you that the verification problem described in this section corresponds to the, in this case, ward test case. And so that relates to the basically everything found in this ward subfolder. And what we're looking at right here, this batch of 5 folders or files, this is a HydroGeoSphere model. If we open up one of these files, a grok file, this is the name of the HGS input file. It's just a text-based file. Right now we're looking at it in a program called Sublime Text. It's just a basic text editor. I have a special HydroGeoSphere language package installed on Sublime Text, which helps to highlight keywords throughout the HGS input file. But ultimately, this really is just it's just a text file. You can open it in Notepad, you can open it in Microsoft Word, Notepad++, whatever you like. But this input file basically contains, well, in this case, if we scroll right down to the bottom, there's 170 lines of commands or inputs which describe the nature of the model. Some of these commands, as you can see here, are related to the generation of model outputs. Other commands are related to the definition of boundary conditions, in this case for heat transfer. Other commands are going to be related to the definition of, here we have some solver parameters, which basically just determine how the numerical solver will operate. The definition here of solute, basically of the active quote-unquote solute in this model, which is just thermal energy. The definition of the grid, definition of material properties, etc., etc. So in this example, 170 lines of text basically describes the entire model. Of course, looking at a text file, which is just comprised of a bunch of commands, doesn't necessarily give a new user a really solid understanding of what this model is. And so that's what the verification manual is all about. It gives you just a couple of, maybe a page or a couple of pages of description of what this model actually what it's comprised of and how to, interpret the results basically. So this is a really helpful manual just to give you, again, a sort of plain English description of some of those example models, and you can really learn from those models. Again, if you're planning on doing a thermal energy transport simulation, well, this input file basically becomes a blueprint for you to modify for your own purposes. And then our third and probably most important manual from a practical perspective is our reference manual. This is by far our largest manual. It's at this point over 450 pages. There's really one key chapter to this manual, chapter 2. It contains all of the input and output instructions, or in other words, it has a description for every individual command that is at a user's disposal to create a HydroGeoSphere model. So this chapter is divided into important subsections on grid generation, selecting mesh components, defining initial conditions, defining boundary conditions, defining materials and material properties, or in other words, your flow parameters. Subsections on winter processes or hydraulic mixing cell or particle tracing, some advanced features, and a subsection on how to generate model outputs. So this chapter here brings us all the way up to at least page 366. So we have a couple of long appendices as well. But this manual here basically describes how HydroGeoSphere works. And really what it is it is a huge compendium of the commands that you can use in your input file. For example, if we open up a grok file here, we can see that there is the command use domain type. What does that actually mean, and how do I apply that in my own models? Well, it's all going to be described in this reference manual. In this case, the command use domain type will then be followed by one of the following strings: porous media, dual, surface, fracture, channel, well, tile, or evapotranspiration. And it essentially just ensures that you are actively working on the correct model domain, right? So if you wanted to start defining boundary conditions for the surface domain of the model, you would start by using this command to make sure that you're actively working in the surface domain. Yeah, so this is a really important reference document for you. I would, as a new user, want to keep a copy of this near at hand as you continue to explore HydroGeoSphere and learn how to build your own models. To learn how to build models, you'll really want to just spend some time reviewing a lot of these example models. And as you come across commands that you're not familiar with, just do a quick Control-C to copy, go to the reference manual, Control F here to search, and then search for that command and just read what it does. We'll come back to the manual here. There's a couple of sort of key things to know about how to navigate and really effectively read that manual. But that's a quick overview of the resources that are available just right there in the installation folder. So we've talked about the 3 manuals. Now let's talk about the really basic bare bones workflow. So whenever you're working with HydroGeoSphere, you're always going to follow these 5 overall steps. First, you're going to write the grok file. You're going to create your model input file. That's a lot easier said than done. There's obviously a lot to learn here in step 1, how to build these input files. But for now, we'll set that aside. You start by building the input file. Then you're going to run a series of executables that will pre-process model input files, run the model, and then post-process model output files for visualization, which brings you to step 5, which is, of course, reviewing and analyzing your results. Let's take a closer look at these key executables. So there's 3 important executables. The first is called grok.exe, and what it does is it basically reads the grok file. So it reads your model input file, and as it reads through that file and encounters different commands that you've included in the model input file, it will basically execute the purpose or the function of that command. Essentially what this does is it reads your text-based model input file and it prepares the matrix of equations for your model. The next one is phgs.exe. This truly is HydroGeoSphere. It's the numerical simulator. It takes your matrix of equations and it will solve it, and it starts to generate nodal outputs and all sorts of results, basically. Most of the output that is generated by phgs.exe is binary. Again, HGS models are very complex, and so every single node in your model domain is going to produce potentially up to 24 or more individual variables, output variables, things like hydraulic heads or saturation levels or pressure heads or velocities and fluxes, potentially concentrations, evapotranspiration rates, etc., etc., etc. Because it produces so much data, all of that data is going to be written to a binary output file, which basically saves a lot of space on your computer. These executables here, hsplot.exe or hgs.vtu.exe, they will read those binary files and they will package all of the outputs up into a single set of output files that can then be loaded into a visualization program such as TecPlot or ParaView. I'll quickly note that this training session is going to look primarily at hsplot. We'll look at hgs.vtu as well. Traditionally, hsplot has been the go-to post-processing executable, but pretty soon we're actually going to be deprecating hsplot and moving forward with hgs.vtu as being the new standard post-processor. They both work the same way, essentially, so it's not really that hard to learn the lessons from one and apply them to the other. So let's take a closer look at this whole workflow. We'll do a live example here. So for now, I'm going to use Abdul, ABDUL. This is our sort of most, I would say, most ubiquitous and commonly used reference model as an example. This model has already been run, so there's all these extra output files. What I'm going to very quickly do is I'm just going to delete this folder, and I'm going to quickly reinstall HydroGeoSphere. It should only take really 1 second or 2 seconds. And this is just going to reset that HGS installation folder to sort of its original state. So let me just quickly reinstall here. It's going to ask me to close this manual. Okay, so that reinstallation there was successful. Okay, so back to our Abdul example. So this is what a model input file or folder looks like in its sort of pristine original state. There's just a handful of input files. There may be some subfolders with key data, whether it's raster files or shape files that may help you to delineate, layer elevations or where property zones exist, wherever the case might be. But you really have this one key input file, which is, again, the grok file. And now every grok file is going to have some similarities, some key components to it. Every grok file will require you to generate a grid, of course, or to define a mesh. And this mesh is ultimately what you apply your boundary conditions and initial conditions and material properties. That's what you map them onto. So every grok file is going to start with the grid generation section. And what's happening here is basically there's a command here to read in a two-dimensional triangular finite element mesh. Then we're starting to define layer by layer, our layer elevations using these GB files, which are essentially just raster files. Scrolling a little bit further down, we have the end of the grid generation section. There will typically be a section here on general simulation parameters. These are basically simple commands that will change the nature of the model. For example, whether the model is going to be run in transient mode or steady state mode, whether we use the dual node or the common node formulation for any particular domain. If you're taking notes, I'll point out that the dual node formulation is always, always, always recommended. So if you're doing an integrated surface subsurface model, you'll 100% want to have this command in your input file. There's another command down here that I'm going to just migrate up here. Finite difference mode. This basically turns on the finite difference approximation to the standard default finite element solution. So you'll generally have a section up here, general simulation parameters. There will then always be some sections of a grok file that are there to define material properties. So we'll talk more about how this works, what the mechanics of defining material properties are, but suffice it to say right here what we're doing is we're saying, hey, use the domain porous media. Here's a file that contains all of our actual material properties, our hydraulic conductivities and porosities. And then we're choosing some zones in our model, and then we're reading the properties of a material type that is defined in this file here. So basically these 10 or so lines of text, they define the porous media flow properties or parameters for the entire model. We do something similar here for the surface domain. So we're defining our land use classification zones and associated parameters, the most important one being Manning's friction coefficient. Moving further, we get to a section here where we're defining initial conditions. This is always going to appear in every grok file because every model requires an initial condition. You're always going to find boundary conditions. These are the mathematical forcing functions that cause water to actually move through the system. You will pretty much always have a section of a grok file that defines numerical simulation criteria. So for these lines here, for example, they define the convergence criteria for our matrix, our iterative matrix solver. Time stepping controls, which define minimum and maximum time steps, that type of thing. And then finally, there will be a section on outputs. So when should we produce a snapshot of model results? Are there any particular points in space where we want more detailed results, specific observation points? And again here, just about 250 lines or so defines the entire model. Many, many grok files will be much longer. It depends on just how detailed your model will be. But pretty much every model is going to contain those similar components. It's going to have that basic, structure. So this is the first step in our workflow, is to build that model input file. This is really where you exert all your control over the model. So, just to say write a grok file is easier said than done, as I mentioned before, but you have over 30 example input files to review and learn from. As well, we have a detailed tutorial with a really highly commented grok file that I'll talk about a little bit later. So you're then going to run grok.exe, and this is what your project folder will look like before you run grok.exe. After grok is run, you're going to have a whole bunch of extra input files. Most of these model input files are binary. They're not necessarily readable by a human, but they define the structure and the contents of the matrix of equations. To run grok.exe, what you'll do is you'll go to the project folder, or in other words, the location where your project exists. You're going to click in the address bar in Windows Explorer and type cmd. That opens up the command prompt. You can also run this from PowerShell if you prefer. You'll then type in the command prompt grok.exe, or you can just type in grok, and you'll hit enter, and it will automatically run grok based on the contents of the current folder that of the active directory. And then when grok is successful, you should see this normal exit message. There may be at times warnings or errors. If you run into an error, grok will fail, and you won't see this normal exit message. You'll have to resolve that error. Oftentimes it's a typo in the input file, for example. But warnings are usually just comments about how, hey, this is an older command that you should maybe update, and usually we'll provide some guidance on how to resolve these warnings. But this is what things look like after you run grok.exe. There is a key output file at this point, the .eco file. It basically contains a persistent record of all of the contents of the command prompt as grok.exe runs. So let's see this in action here. So again, you just navigate to your project folder. And by the way, you should never save any of your own projects into the HydroGeoSphere installation folder. We have a bunch of example projects here, but this installation folder should not be used for your own projects or for your own data. It may at times be overwritten, and so just don't save your own stuff in this folder. You can, of course, save projects and input files anywhere on your PC, so just don't do it in the installation folder. So you'll navigate to the location of the project, basically where that grok file sits. And again, just click in the Windows Explorer address bar, type cmd, hit enter, and that opens up the command prompt here. And what we're going to do is we're going to type in grok, and we'll see a couple things happen all very quickly. It usually doesn't take too long for grok to run. What we see here in the command prompt is a line-by-line echoing of the commands that the executable grok.exe encounters within the grok file itself. So as you're going through, if all of a sudden you encounter an error right here, you can go to the previous lines, and that will basically give you a sense as to how far through the file did grok.exe get before it encountered an error, which can be really helpful for troubleshooting. Over here, right, all of these input files have been generated. The important one at this point is just the echo file, which just basically contains a persistent record of essentially the same information that you find in here. It's a little bit more detailed in this echo file, but it's also just kind of echoing line by line, command by command, what grok is encountering in the input file. The other nice thing about this .eco output file, if you do a quick keyword search for summary, once grok is finished and it has that normal exit, it will then write a summary of your model inputs. So everything from units to a summary of the mesh. So you can use this to just check, hey, do I actually have the right number of layers that I expected? Is the geometry limits of my model what I expected? how many nodes there are, and then we get into mesh quality statistics. So when you have a triangular element mesh, it's very important to have a highly optimized and high quality mesh to maintain faster model runtime. So we've got some information in here about that. As you go further, right, there's just a summary of the porous media, the properties that have been applied to the elements within the model. And moving further, you get a similar information for the surface domain and any other active domains. There'll be a little bit further on a summary of boundary conditions, et cetera, et cetera. I think you get the idea. So this is a really helpful file at the early stages of just running grok.exe. You can use it as a way of just checking that your model was constructed to your expectations. The next step in the workflow is to run phgs.exe. So this is also done here in the command prompt. You'll just type in phgs. We'll scroll down to the bottom here and we can type in, oh yeah, as I mentioned before, warnings are usually something that are worth addressing, but they're not fatal errors, right? So here in the command prompt, by the way, if you ever close it, that's not a problem. You can just open it again. All of the input files that you need to run phgs, they're still here in your model folder, so no need to run grok again, unless you make any changes to your grok file, in which case you would need to save the file and run the model or run grok again. But to run the simulation here, we're just going to type in phgs and hit enter. And I'm going to allow this to go for a second, but I'm going to try and just pause it. Oh, right, never mind. I forgot about how you're not allowed, you can't really pause it with Windows 11. Well, in any case, it's still running, but what we're seeing here in the input or in the command prompt is basically time step by time step, right? Repeating pattern of information, which basically contains three major sections. First, there's this global target time update, which basically tells us the progress of the simulation. How far along is it done in terms of the percentage of the total simulation duration? What's the current time? What's our time step size? Things like that. Then we get into this section here, the summary of nonlinear iteration. This is basically giving us information about the Newton iteration iterative solver that is used to actually solve the system of equations. Key information here are the del val and the res val values. These are basically the Newton residual res val and the Newton absolute del val convergence criteria. When one of these convergence criteria is satisfied, then it's assumed that the solution is accurate enough to move to the next step. So really, these are the goalposts that HydroGeoSphere is looking to aim for in terms of model accuracy as it goes from one time step to the next. And then after a time step has been solved, the adaptive time stepping routine steps in. So in HydroGeoSphere, you will typically define an initial time step size, and you'll also define a number of, I'll just open up the grok file to show you. You'll typically also define a number of control targets. So here we have a defined head control, saturation control, and Newton iteration control. What these numbers are basically saying is that in terms of head, this tells HydroGeoSphere that we don't want the head in any node in the model to change by more than 0.5 meters from one time step to the next. This is basically the upper speed limit on how fast HydroGeoSphere will run. So HGS will automatically try to increase time step sizes as long as these control targets are not exceeded. So at every time step, what HGS does is it loops over every node in the entire mesh, and it finds out where the maximum change in any of these control variables occurred. So in this case, there was a head change of 0.16061 meters, and that happened at node 20,953. And we have a target change of 0.5. So these two numbers are basically divided one against the other, and HGS comes up with a suggested time step multiplier. If all things were equal and we're only looking at hydraulic head changes, basically HydroGeoSphere is telling us that we can increase the time step size by a factor of 3.11. And in the next time step, we would only still expect to see a head change at some node of 0.5 meters. So HGS does this for all available control targets, and it will eventually identify the smallest time step multiplier, and it's going to use that one. So that's the lowest common denominator in how fast the the time step should grow. In this case, though, we've also defined, I think, a maximum time step of 100, and the current time step is already 100. So in this case, it says, okay, well, the step is solved. We're going to go to the next time step. We're going to multiply our time step of 100 by this time step multiplier of 1.5. Our next time step will be 150 seconds. Oh, wait, that's larger than our maximum allowed. So it'll just defer to the user input, right? And then it goes on to the next time step. So 8.3% done, t equals 500. We're doing a 100-second time step. And it goes through the same pattern of outputs. Every now and then, though, when you solve the system of equations at a specified output time, in this case t equals 600, you'll also see a bunch of information here where it says saving saturations, saving volumetric water content, saving heads, saving pressure heads. What's happening there is it is actually saving a large batch of binary output files. So I believe t equals 600 was the third output time that we defined. We had t equals 1, 300, and then 600. And so when you see all of these lines being written in the output, what's actually happening is the batch of files that I'm currently highlighting here were saved. And so each one of these files contains one of the variables that's listed here. So the naming of these files follows a bit of a convention here. So the name of the project itself is Abdul, and then we have O for output, and then we have dot head. Head here is a variable, and then underscore OLF. That stands for overland flow. So these are the heads in the overland flow or the surface domain. And then dot 0003, because this is the third of our output times. Similarly, we have here head underscore PM. That's head in the porous medium. We have max underscore depth underscore OLF. So that's the maximum flow depth in the overland flow domain at each individual node. Sat underscore PM. These are saturations. So all of these individual variables are saved into their individual output files, and these contain a snapshot of that particular variable at all nodes within the particular model domain. But as I mentioned before, they are binary, so they're not human readable. And excuse me, that brings us to our penultimate step in the workflow, which is to, again, you have binary outputs. So what we want to do now is to run hsplot.exe or hgs.vtu.exe. Before I do that, I just want to highlight one key output file when you run PHGS, and that is the .lst file. So this file is what we call the list file. It similar to the echo file, it's basically a persistent record of the information that's saved or shown here in the command prompt. Okay, so you have information about your global target time update, your summary of nonlinear iterations, so your Newton convergence or iterative solver. You then have information about fluid mass balance at every output time. So that information isn't shown in the command prompt, but it's saved here in the .lst file. And then you have your adaptive time stepping updates and then on to the next time step. The water balance information that's saved in this file is ultimately the source for information like a more focused water balance output file. So there's a series of files beyond the binary files that are generated every time you run HGS, including this file here. It's a water balance file. It contains for every individual time step. Excuse me. I'm just going to zoom out here so that you can see that it really is just a time series file. So the first column here contains times, and then you have all these other variables related to boundary conditions, and then your net boundary condition fluxes, changes in storage in all active model domains. Finally, the net accumulation or the net storage change across the entire model, Then you have some error statistics, and then finally you have some statistics here on fluxes between model domains. So OLF to PM, for example, is how much water has flown from the surface into the subsurface. And then PM to OLF, of course, is the opposite, how much water has exfiltrated from the subsurface into the surface. So, yeah, so you have this LST file. It's again like a persistent record of the information that's shown here in the command prompt. So we're going to scroll to the bottom here. This model did eventually solve successfully, and so you also get this normal exit message. And now our next step is to run hsplot, and what it's going to do is it's going to take all of the binary output files, every file that I've just selected here, and it's going to basically package them up into a single one output file per active domain. So basically it's just created the abdul.o.pm and abdul.o.olf. Both of these have a .dat file type. So it's just created, where did they go? Oh, here they are. So it's just created these two files. And now if we open up these files, they are very, very large, but they're TecPlot formatted files. So they contain up here a whole bunch of metadata identifying individual variables, units, and variable names. And then it's in a block formatted format. So not a simple time series. First you have information about all the X coordinates for every node. Then eventually it will list the Y and the Z coordinates. And then it gets into listing individual variable values or output values. And anyways, it's a really, truly large file. It's, as you can see here, almost 800,000 lines. So this can be, you could potentially use that if you're a coder to potentially extract information. But that file itself is actually formatted for visualization in TecPlot. So TecPlot is quite expensive, and we recognize that most of our users may not want to necessarily buy a license. It does create extremely high quality figures, and it has a lot of really nice features when it comes to visualizing and working with HGS outputs. But there is another program, ParaView, that is 100% free. It's open source software, can be downloaded by anybody. And that can also be used to visualize model outputs. I'm not going to spend very much time today talking about visualizing model outputs just for lack of time. But in a nutshell, here we've loaded in our model results. Right now we're just looking at the model mesh and our zones. So there are 3 zones in this model, at least for the subsurface. We can then change the contour data. Rather than showing zone, we could perhaps show soil saturation. Now this is a fully transient data set, so we can see how the soil saturation changes over time. We can look at all sorts of other output variables as well. Velocities, depth of groundwater. You can have your material properties here, so porosity values, et cetera, et cetera. Then you can do the same with your olf.dat output file. So here we can just load it in quickly again. We can display this in 3D Cartesian space. So the surface domain, the vertical exaggeration here is really high. You can maybe change that a little bit. But it's a pseudo 3-dimensional zone, right? So every element, every triangle, every tile in this mesh is 2-dimensional, but altogether they create a quasi 3-dimensional model domain. And this is just draped on top of the porous medium domain. But similarly, we can look at output data. Right now it's just showing zones. We can look at hydraulic heads or surface water depth, for example, and see how those change over time. All right. TecPlot can also be used to create cross sections, isosurfaces. It can be used to we can load in, for example, our time series output, perhaps our water balance file, for example. Load that in here. So TecPlot is really, really helpful, but again, quite expensive. So we'll set this aside and we'll just very briefly also demonstrate how to visualize things in ParaView. So here what we would do is simply write HGS to VTU and hit enter. And here, rather than creating a single output file for each domain, it creates one output file per output time for each model domain. But if we open up ParaView, we can actually just select all 9 of these and drag and drop them into ParaView at once. So there's ParaView. We just drag in these files, click this little button to visualize, and again, it's full 3-dimensional model outputs here. We can look at surface with edges to show our wireframe mesh where our elements exist. And we can then start changing which variables we want to look at. And this is also a fully transient data set, so we can see how saturations change over time. Again, the purpose of this course is not going to be to focus on the visualization, but there is a comprehensive tutorial document included in the training materials that has more information on the basics of visualizing model outputs here in ParaView and TecPlot. All right, I'm going to set that aside for now, close up all these windows, and just highlight that this has sort of been a very quick overview of the most fundamental parts of the HGS workflow, right? How to actually run the models and key outputs at each stage. So when you run grok.exe, right, there's that prefix. We use this terminology prefix O, prefix just meaning the name of the model, the name of the grok file. For the example shown here and the example that we've just looked at, prefix would be Abdul. So when you run grok.exe, you have the .eco or the echo file. When you run PHGS, key output files include the list or the LST file, your water balance output file, which contains the detailed water balance tracking for every time step. There will also be these prefixo.variable_domain.xxxx binary output files. Each of these files containing an individual variable. Sorry, just saw a typo there. Individual variables at each indexed output time. And then, something I didn't mention, but if you have observation points, for example, you've defined particular key points in your model that you want to have more detailed output, there will be individual output files generated for those. Same thing as hydrographs, or there's many commands related to generating model output that I kind of glossed over, but we'll see more examples of that as we go through a more detailed overview of a grok file. And then, when you run hsplot.exe, again, just remember that you get this one output file per active domain. So you would have a prefixo.pm.dat and a prefixo.olf.dat. If you ran a fracture model, you would also have a prefixo.frac or frac.dat, frac standing for fracture. Whereas for HGS to VTU, it's going to create one output file per domain per output time. Those can all just be loaded in, though, and then you have similar visualization capabilities in ParaView or TecPlot. All right, so for the rest of the training session today, I'm really going to do a deep dive on grok files. So reviewing all of the key portions of a grok file, as I mentioned before, there's always grid generation, there's always definition of boundary conditions and initial conditions. We always have to define materials or the properties and parameters for our governing equations. We will always have to define outputs and some numerical and time stepping settings. So all of these are common sections or components of a grok file. We're going to go through this, step by step here and kind of really try to demystify things a little bit, because just reading through these text files can sometimes be a little bit confusing, or it may seem a little esoteric. But we've actually made a good effort, I think, with HydroGeoSphere for all of our commands to be relatively plain English. So for example, the command choose nodes all, you can probably guess what it does. The command initial head followed by a numerical value, you can probably also guess what that does. So while this may look a little bit like some sort of complex scripting coding language that's unique to HydroGeoSphere. And technically it is a sort of a unique command-based language for HydroGeoSphere. It's not as complex as it really seems at first glance. So this is really going to be the focus of the rest of the session today. I'm going to suggest we take a short 5-minute break here just so I can grab a little bit of water. And if anybody needs to take a little bio break. It's 2:13 now, so I'm going to plan to get started again at 2:18 sharp. Hey everyone, it is 2:18, so we're going to get started again here. Now, as we move through the rest of the training session and take a deep dive on grok files, I just want to point out that the input files, or the grok files, typically associated with these verification problems, if you open any of them up, you'll notice that they usually have some comments, but not a tremendous amount of comments. So as part of the training session and part of the package of training materials that were sent out to everyone, included in that would have been a copy of the comprehensive Intro to HydroGeoSphere tutorial. So this tutorial package, I'm going to actually just extract a fresh copy so that we're all working from the same starting point. Not that I recommend that anyone work through this right now, just feel free to sit back and watch. But in this intro tutorial package, you'll have a detailed guidance document, so a PDF here that's about 90 pages long, and it takes you through the full HydroGeoSphere workflow from building a model mesh, and this is typically done using an external program called AlgoMesh. This is not part of the training session today, but we do have a YouTube video that's about 2 hours long, focused only on building meshes with AlgoMesh. So this isn't really covered in today's session, but it is covered as part of the tutorial. If you don't have a license of AlgoMesh, or you would like a temporary license of AlgoMesh, feel free to just reach out to me and ask. I'll connect you with the developers. So there is a portion of this that is dedicated to AlgoMesh, but in addition to this detailed guidance document, there's also a working model. And so this model includes the outputs from AlgoMesh. You don't necessarily need to actively have a working copy of AlgoMesh to complete this tutorial. But the grok file, so the input file for this tutorial, is very, very heavily commented. So in a HydroGeoSphere input file, you can use exclamation marks to add comments. So all this grayed out text that you see, these are all comments that I've added specifically to sort of describe what is happening line by line by line. So this grok file, this model input file itself, is extremely valuable as a learning tool, and I would suggest this should be the next model that you sort of take a deep dive on. If you want to really continue to learn about HydroGeoSphere, then get a copy of this PDF open and just start reading through it page by page, and have a copy of the grok file open so that you can follow along. The document, the grok file itself and the tutorial guidance document, they're both they cross-reference each other quite a lot. So again, this tutorial covers the full workflow from part 2 here, building the model mesh with AlgoMesh, to part 3, configuring the grok file or writing the grok file. It goes through all of the key sections of a grok file that we're going to be talking about in the next hour and a half or so, and highlights key commands and inputs that users can use throughout. Then part 4 is really an overview of running the model. So the key, the key executables, grok.exe, phgs.exe, etc. So basically that part 4 is a recap of everything that we have talked about thus far in today's training session. Finally, part 6 is dedicated to visualization of your outputs with TecPlot and ParaView. And then finally, part 6 has sort of next steps for things that you can explore. A question just came in, a really good one. Oh, actually, there was a second question earlier that I didn't quite see about 5 or 10 minutes ago. All right, so the first question is, what software do I need to download to use the graphical version of HydroGeoSphere, and can we use it with a trial license? Very briefly, I'll explain that. What you would want to do is you would want to Google Aquaveo or go to aquaveo.com. They have this program here, groundwater modeling system. And if you go through their website, you will eventually find, somewhere to request a trial. Let's go to, here we go, free trial, just up here. So what I'll do is I'll put this link directly into the meeting chat here. And when you email them and request a trial, just make sure that you tell them that you're interested in the HydroGeoSphere interface particularly. And as you then go to trial the GMS interface, this is what's actually shown right here is a picture of our R5 tutorial. So the model that we're about to review, that's a picture of that right there. In any case, if you do get an access to a trial version of this graphical user interface, you'll also want to access some of their tutorials. So if you go to learning, there's a section or a page for GMS tutorials. And then if you go over here to this additional tab, you'll find the HydroGeoSphere focused tutorials. Again, this does require an additional add-on interface to GMS, but the people at Aquaveo can walk you through all of that. And finally, what I'll point out is on Aquanty's YouTube channel, I hosted a webinar in January of last year where I introduced the new interface. So you'll find that video right here. This video, it includes a live demonstration of the interface itself. So that's what you're seeing here towards the second half of the video. But it also includes just a short presentation initially that looks at key components of the GMS interface and a quick overview of how the HydroGeoSphere workflow has been integrated into this program. So I will include a link to this video in the chat as well. And then a second question, a follow-up question. I've installed ParaView, but it does not show the output. What does that mean? So when you generate output in your HydroGeoSphere model file, I'll just go back to the example that I was looking at before. It's going to create, when you run HGS to VTU, it'll create these VTU files. And then when you load them into ParaView, you have to click a little eyeball button next to the particular data set up here in the pipeline browser. So if you drag this in, you don't currently see anything, but there's a little eyeball right there next to the data set. You'll have to click that to turn it on. This is all outlined in detail in that detailed tutorial guidance document. Okay, and then another question came in from Sebastien. We can't build the mesh without AlgoMesh. That's not necessarily true. You can. There are plenty of free triangular element mesh generators out there online. I do recommend, we do highly recommend AlgoMesh because it produces highly optimized, high quality meshes. It really provides the best algorithms for generating these meshes, and having a high quality mesh can be very important when you're working with HydroGeoSphere. Now, with that being said, you can use pretty much any mesh generation program you like. The only requirement would be to take the outputs from whatever mesh generating algorithm you use. You would need to modify it so that it fits into the AlgoMesh output format. And what I have right here, this .ah2 file, this is an AlgoMesh mesh file. It's exported from AlgoMesh and is ready to go right into your HGS input files. But you can open this with any text editor. So we'll open it in Notepad. And the structure of this file is quite simple. It just lists the total number of nodes and then the exact coordinates of each node. And then as we scroll further down, it will then transition to information about individual elements, mesh elements. So nodes above, and then it lists the total number of elements and the index numbers for individual nodes associated with each element. This type of information, in my experience, is generally easily accessible and exportable from other mesh generating programs. And so it's usually not too difficult to generate a mesh using some other program and then just simply massage the data into this format, save it with a AH2 file file type, and then you can use it with HydroGeoSphere. I can walk you through that process. I have instructions that I can send out in an email if you like. Just email me about that, and we can kind of handle that another time. And so Miriam mentions that for ParaView, it seems that clicking the eyeball thing doesn't work. I would next try to click the apply button, and if that still doesn't work, I would say let's have a follow-up call sometime. I'm not exactly sure. We can get together and try and troubleshoot that. But usually it's quite simple. You just drag and drop the data in, and then click this button to turn it on, basically. And I see one other person typing, so I'll just give a moment and I'll answer that question now as it comes up. Maybe it's a longer question. Oh, here we go. How did I apply the color scheme in Sublime Text to visualize the grok file in color? That's also a good question. I will point out that in the first section of the tutorial, there's an introduction that talks about software requirements as well. And here there's going to be a little mention of how you need a text editor. If you click on this hyperlink here, it will open up the GitHub page for one of our users who generated the HydroGeoSphere language grammar package. This website has instructions on how to actually install this language package. So I use Sublime Text. It may be different if you're using a different, if you use TextMate, for example. But generally, you'll just follow these instructions, and it will. If you have any trouble getting it to work, again, I'm happy to hop on a call with you at some point. But I'm gonna just leave this link here in the chat, and that way you can kind of work through that on your own. All right, so back to our presentation here. The rest of this training session is focused on grok files and basically building your grok files. First thing I'd like to point out is that almost all aspects of the model setup are controlled through the grok file, so you'll spend a lot of time managing your grok file. It's based on a command-based language that is relatively intuitive. I think most of the languages, or the commands rather, are just in plain English. You can use exclamation points to insert comments for documentation purposes, always a really good idea. There's key sections to a grok file, all things that we've talked about. I just had one other thought that I wanted to mention, but I guess it'll come up later. Oh, yes. What I also wanted to point out is that this grok file here, the one for the tutorial, it has a ton of commands in here that we recommend as using sort of as your default settings. So, for example, no nodal flow check, finite difference mode, dual nodes for surface flow, transient flow, unsaturated. These are the recommended settings. And so the other thing too is that every grok file, because they do follow the same sort of layout, you can mix and match the sections in whatever order you want, but they all have the similar contents. And basically what I wanted to say is that there's not really any value for a new user to create their own grok files from a blank text file. As you're building your own models, feel free to just take any existing grok files, this one included, and just start swapping in information. For example, rather than reinvent the wheel and write out this whole section on creating the model mesh, you can just swap in file names to swap in your own data, right? That goes for everything from the triangular element mesh to the raster files used to define layer elevations to anything really. So yeah, that's something I want to mention, is that most users don't really write these files from a blank document. It's usually a lot easier to just take an existing grok file and modify it for your own purposes. Okay, every grok file, I mentioned earlier, you can mix and match the sections of a grok file as you please, but there are two rules. The first is that every grok file must begin with a problem description. This problem description is really just a section for taking some notes, and it is terminated or ended with this end title command. Everything above here is just comments, and every grok file has to have at least one line of text followed by this end title command. So every grok file starts with a problem description. Feel free to leave as much or as little information in there as you like. Then, before you begin to define boundary conditions or initial conditions or anything like that, you will need to define the grid. So this is the next section of the grok file that must be completed. And that's because, yeah, you can't really define the model without first defining the structural sort of mesh upon which all aspects of the model will be mapped. So in HydroGeoSphere, or in your grok files, you can define meshes directly using commands like generate uniform blocks. This would end up defining something like what we see on the bottom right here. You can also get a little bit more detailed. You can use commands like generate blocks interactive, which is what we call a command block, because it is going to be, there will be a number of commands that can be contained within it in this nested sort of command block. So some commands will have like a command name that then has to be quote unquote ended somewhere later in the grok file. And then you at times will have these commands that are unique to that sort of context. So here the generate blocks interactive command allows you to then invoke these grade X, grade Y, and grade Z commands only in this particular context. And they end up allowing you to generate sort of variably refined grids. So I think it's a good opportunity. I usually like to just highlight over these two slides. I'd like to revisit again the reference manual to just highlight the overall structure of and formatting of the reference manual. So again, if you ever encounter any commands you're not familiar with, let's say it's generate uniform blocks, you should take the moment to look it up in the reference manual. And so the structure of the reference manual, it's basically hundreds of pages that looks kind of like this, where you have a solid line, which indicates that we are about to define a new command. The command name itself is shown in this unique formatted like text format. And then some commands require you to have additional lines of input. Some commands are just one line. You know, you say transient flow, or, you know, as an example, you might have a command that like unsaturated. This is a one-line command that turns on unsaturated flow rather than the default saturated flow. Other commands require you to provide additional input variables. Generate uniform blocks is an example of that. This 1, 2, 3 tells us that there needs to be 3 lines of additional input for this command. And then individual variables are listed on a line-by-line basis, xlen, nbx, and x0. And then you have an English, just a description of those. So xlen, that's the domain length, and nbx, that's the number of blocks in the x direction. And then optionally, you can define an origin in the x direction as well. And then you just repeat that in the y and then in the z dimensions. And then you get a plain English description of what the command does. In this case, it generates a grid for a rectangular domain made up of uniform blocks, etc., etc., etc. ... means the end of the command description, and then we go straight on to the next command. Okay, so this is, again, the reference manual. It's hundreds and hundreds and hundreds of pages of commands, and these are your basic tools, right? These are the building blocks for you to build your HGS models. If we visit again our input file, or sorry, our slides, we can take a look at generate blocks interactive. As I mentioned before, it's an example of what I call a command block, or a command that will have sub-nested commands and has to then be at some point, quote unquote, ended using an end command. So generate blocks interactive causes grok to begin reading a group of interactive block instructions until it encounters an end instruction. The group should contain at least one instruction for each of the principal directions, and then it lists the available instructions, grade X, grade Y, and grade Z, as we saw earlier. And each one of those then requires one additional line of input. So the starting x coordinate, x1, ending x coordinate, x2, the starting element size, dx start, x FAC, the element size multiplication factor, and then dx max, the maximum element size. So putting all of these together, you basically are saying, like for this first line, it's saying starting at x equals 75 and all the way to x equals 0, we will start with a mesh, like a block that is 0.01 meters wide. Each neighboring block will be 1.5 times wider until we get to a maximum block size of 5 meters. And if you just chain all of these commands together, you get this variably refined mesh that you see in the bottom right. So these can be really helpful if you have a model that is, perhaps limited in scope and doesn't have any irregular shapes or boundaries that need to be applied to it. More often than not, though. So again, you can define these sort of simple grids directly in HydroGeoSphere, but more often than not, you'll need to use a triangular element mesh in order to represent irregular geometries. So that's again where AlgoMesh comes in. The benefit of using a triangular element mesh is that you can easily refine in areas of interest. So for example, along a road network or a stream network. And the mesh will conform to your boundaries, so you don't have to have, a rectangular model itself. The model itself can be completely irregular. So again, we do recommend using AlgoMesh, but as we talked about, there are plenty of other options out there that can also be used. So when you do create a triangular 2D triangular element mesh, that's usually going to be read into your grok file using this command here, read AlgoMesh 2D grid. What we see next on the next line is basically we have to point to the file itself, the actual AlgoMesh output file. I usually like to point out that what I've included here is a relative file path. So in our project folder, we have a mesh subfolder, and the mesh subfolder is what contains the actual mesh itself. So when we include the key characters ./, that basically says relative to the current project folder. So starting here, you will find a subfolder called mesh, and then / in there you'll find r5_mesh.ah2. You can also build relative file paths that look in the opposite direction. So for example, if I wanted, I could take this mesh folder and I could save it out here. And what I would then need to do is just change this to .mesh. So this says from the current project folder, which would be again r5_model because that's where our grok file is. // means go up a folder and then look for mesh. So I'm just going to put this back because otherwise it will require some other changes to the overall input file here. But this is really how the two-dimensional triangular element mesh is read into HydroGeoSphere. That's how you get this going. Once you've got a 2D triangular element mesh, you then need to start defining the vertical structure of your mesh. So this is typically done using this command here, generate layers interactive. And I should add ... end because this is in fact a command block. And this is usually the component or the section of a grok file that gets structurally the most complicated. There's going to be, as soon as we exit the problem description, we are by default in the grid generation section. We have another end command here that's related to the generate layers interactive section. And then we have another set of nested commands here, or command blocks, to define base elevation and generate new layers. So structurally, this is the most complex that a grok file will get. But basically, we use the command generate layers interactive that allows us to start building the vertical dimension of the mesh layer by layer by layer, starting from the bottom and working our way up to the ground surface. And there's a number of different individual commands that can be used to define individual layer elevations. If I make this a little bit larger, you can see here we have this snippet of a grok file relates to this black and white mesh over here. We have generate layers interactive, and then we've got, base elevation, where we define an elevation constant of 0. So that's basically the bottom of the model. To define a new layer, we just simply have to define the top, right? Because the bottom is defined as an elevation constant of 0, and now we have to just define the top of layer, the first layer. And so that's done using another elevation constant command. And then it's also subdivided into 15 uniform sublayers. So that's basically everything from here down. And then, here we're on the next sort of structural chunk of the layers are defined using the command elevation from xz pairs. And here we basically just provide a list of x and z coordinates. And HGS will just read through and interpolate based on the x coordinate of an individual node and where it falls in this list, what the z coordinate should be. So if you're interested in using something like that, again, just look up the command name itself in the grok file or in the reference manual, and it will explain sort of the functional components about how that command works. More often than not, especially with a real world model, people are going to have access to a ton of borehole data or otherwise have some three-dimensional conceptual model of the subsurface. And people will more often than not just define elevations using raster files. So a raster file, of course, is just a gridded data file, something like we see here. So every grid cell in the file contains some numerical value, and that value can be elevations, or it can be hydraulic conductivities, or it can just be zone numbers. But basically, this is a pretty common practice of defining model elevations. So in our example tutorial model here, we start with the base elevation using a raster file. We then have this command here, minimum layer thickness with fixed top elevation. What this does is it basically ensures that there will be no pinch outs in your mesh. I oftentimes like to point out that if you Google Aquanty tutorial, for example, on our blog, we have a whole category. And this category contains tons of these command of the week posts. And these often will highlight specific commands or features or capabilities. We have one that I usually like to pull up around this part of the training session. Let's just see if I can find it. Aquanty minimum layer thickness. So this minimum layer thickness with fixed top elevation, it ensures that there will be no pinch outs. Every model layer in HGS has to be continuous. You can't have zero thickness layers. So something like this, if you're defining your mesh using a raster, so this is just a side view, this would violate the mesh rules. And so these fixed minimum layer thickness commands will simply modify the upper or lower raster to maintain some minimum desired thickness. So in this case, minimum layer thickness with fixed top elevation will move any lower raster further down. So it keeps the top layer fixed in place and simply modifies the nodal elevations of lower rasters to maintain that minimum layer thickness. And we then carry on with these new layer command blocks. So uniform sublayer, we define the elevation using a raster file, and we just repeat this process, and basically stacking layers one on top of another. Most of these are using the uniform sublayering command to split each layer into two uniformly thick sublayers. In HydroGeoSphere, this term sublayering is simply a term of convenience in this component portion of the grok file. If you create a model that has two uniformly thick sublayers, then the model has two layers, right? It doesn't have one layer and two sublayers. It just has two layers. So this is just a term of convenience, basically. Same thing down here with proportional sublayering. This is basically just saying that we will have three sublayers in this region. The upper one and the second will have the same proportional thickness, and then the third will be twice as thick as the upper ones. There's also a command here, offset top, which basically takes the elevations defined in this raster file and just offsets them by -1 meter. So you'll notice that both of the upper layer units were defined using the same raster file. This raster file basically defines the ground surface. So the top of this layer is by definition equal to the ground surface minus 1 meter. And then this section here actually contains 3 layers within the uppermost reach of the mesh. Anyways, you then end grid generation, or sorry, end the generate layers interactive section, and then we end grid generation. Excuse me, and then finally, with respect to meshes, we have this helpful command, mesh to TecPlot. And what this does is it exports a mesh to a TecPlot formatted data file, which can then be visualized. We don't have to necessarily build the full model before getting some visual sort of aid to help us with the overall model construction. So if I add this command here, skip rest, what it will do is skip the rest of the grok file. And when I run grok here, it's going to process the grid generation components of the input file, and then it will output a file called r5mesh.dat, which I can then visualize in ParaView or TecPlot. And then I'll turn on surface with edges. And so this is basically, this is the structure of my model. You can see, if we zoom in on the sides, you can see how there are layers that are uniformly thick. So these 2 bottom layers are uniform thickness. The third and fourth layers are uniform thickness. There's a very thin model layer here. It's kind of hard to visualize, but somewhere on the interior of the model is like a clay lens, and so that clay lens sort of pinches out to 0 thickness, but you can't actually have 0 thickness layers, so that's why we have this very, very thin layer here. I'm just going to close this. I'm going to visualize this in TecPlot because it will help us a little bit to see those different property zones. In the meantime, we have a question. Can we add an area that doesn't take up the entire length of the layer, like a block with different properties in a layer? Yes, absolutely. There's nothing that says that every layer has to have the same properties. Every layer must extend throughout the entire sort of stretch of the model. You cannot have layers that pinch out to 0 thickness, right? But if you have a layer that, like a hydrostratigraphic soil layer, that doesn't extend throughout the entire length and breadth of a model, that would be one area where you would use, like that's basically the situation with the clay lens here. Let me just very briefly, I'll load it up and just highlight what I mean. Okay, so if we zoom it right in here, again, we can see that there's a very, very thin layer here. And that's because somewhere right around here in the model, there's a clay lens that gets thicker, but it only exists here. So everywhere else, we still need to maintain that layer, but it can't be 0 thickness. If we turn on a slice and place the slice, let's put it in the Y plane, put it right about there, and we'll turn the shade and the mesh off. Okay, so what we're looking at here, you'll notice that around here we have an extremely thin layer. And then as we get over into this region here, it kind of gets wider and wider. So this element here, and all the way over to here, this is the clay lens. What we will end up doing in the grok file is we'll define these elements as having one set of properties associated with the clay soil. But then as we move over here, where the clay lens is pinched out, these very, very thin layers, these very thin elements, they will adopt the material properties of either the upper or the lower soil unit, right? So you can't have a layer that doesn't take up the entire length of the mesh, but you can define spatially varying material properties within a layer to your heart's content. So that basically brings us to the end of the mesh generation section, right? But just to highlight again that this is a section that's going to typically require you to rely on a couple of external data files, right? AlgoMesh input files, whether they be the mesh itself. And then raster files are ubiquitous. They're very frequently used to define model mesh geometry, especially the layering. You can also use shape files in many parts of a grok file. They can just typically be used to help you select individual nodes or groups of nodes or elements to define a particular property zone or the location of a boundary condition. Yeah, so let's move on to the next section, which is general simulation parameters. So this basically is used to define the general nature of your model. Typical commands include transient flow. By default, HGS will attempt a steady state simulation, but that doesn't ever really work. It just can't be done with a fully integrated model. So transient flow is going to be something that you include in 100% of your models probably. Unsaturated mode, or the command unsaturated, it turns on unsaturated flow. By default, HGS will run in fully saturated mode and effectively becomes like a mod flow clone. But if you want to run a surface water groundwater model that's integrated, then it has to be unsaturated. So this is also something that's going to be present in 99% of models. This command here, again, if you're taking notes, highlight this one, no nodal flow check. The nodal flow check is especially important for solute transport simulations. It ensures that there's no spurious minima or maxima in the concentration field. If you're not running a solute transport model, or even if you are running a transport model, the nodal flow check is often not really necessary, and it will slow things down a lot. So you almost always want to include this command here. Finite difference mode. This basically changes the solver behavior a little bit in a subtle way. It will improve model runtimes. We generally recommend including this command as well. And then finally, there's commands for all quote-unquote secondary model domains. So the porous medium is pretty much assumed to be active in every model. If you activate surface flow, if you include the surface flow domain, then you will want to include this command here, because what it does is it basically superimposes a dual node for surface flow on top of the node for porous medium flow. Okay, so just coming back up here for a visual aid, what it basically means is that you'll have one node here and another node here, and they're separated by some virtual distance. So the blue check lines here, these are a coupling length. In reality, the nodes for surface flow and subsurface flow, they are superimposed on the exact same location, but they're separated by a virtual distance, which is what allows for explicit exchange of water between the surface and the subsurface. So if you're going to be running an integrated surface and subsurface flow model, you will want to include this command, dual nodes for, in this case, surface flow. Yeah, and then, there's another one that's important as well, do transport. You can define all the transport boundary conditions and properties and initial conditions, but if you forget to include the key command do transport, then the model will just basically ignore all of your transport inputs. Okay, so this is an easy section, but it's a very important section. These are all just one-line commands that don't require any additional input, just one-line option commands. I see a question from Miriam. How long can the total depth of soil for simulation, can we limit it to, for example, 2 meters? The size of your model mesh, including the vertical distribution of layers, is completely up to the user. You can build a soil column model that is 1 meter deep or 2 meters deep or 2,000 meters deep or 2 centimeters deep. That's also true for like a full watershed scale model. If you build a watershed scale model that may be 2,000 square kilometers, you can limit it to being 1 meter below ground surface, or you can have it be 100 meters deep or a kilometer deep. It's completely up to you. So I'm not sure. Hopefully I understand the question, but basically just the geometry of the model mesh itself is completely user defined and there's really no limitations. Now, all of the subsequent sections of a grok file, whether it's defining initial conditions or boundary conditions, property zones, specific model outputs, they all require you to be able to confidently select mesh components at the right location, right? If you want to define a boundary condition in a particular location, you need to be able to work with the mesh, but that can often be difficult, of course, because it's all based on a text-based input file, so you don't really have a graphical interface to just point and click at a particular node. So there's a huge portion of the reference manual, section 2.4, that's all about selecting mesh components. And if we scroll, we can begin scrolling through. Like this subsection here on selecting nodes is probably 20 pages long, all on its own. So there are many, many, many commands that can help you to select nodes using different techniques. For example, when you create your mesh, there will be zones, right? By default, when you create a mesh, it's all zone 1. But then as you go along, we'll see shortly when you're defining material properties, it starts usually by creating a geographically distributed set of zone numbers. You can choose nodes based on those zone numbers. You can choose nodes based on node sets. So node sets come up later on when we'll talk about boundary conditions. You can choose nodes using polylines. You can choose nodes using lists of numbers based on the sheet number. You can choose nodes that are active or inactive around a boundary of the model. You can choose nodes using just the top boundary command here. We'll choose nodes around the top edge of the surface flow domain. You can choose all surface flow nodes, so basically all nodes that are flagged as surface flow nodes will be chosen. You can choose nodes using list of XY coordinates. You can choose nodes using lists of node index numbers, using shape files, using AlgoMesh output files. There are many, many, many commands, right, for choosing nodes, as well as for choosing segments and faces and elements. So this is a really important part of the manual, although it seems basic, and it's a really important part of working with HydroGeoSphere models, is just being able to select the correct nodes and elements based on what you want to do. It's also worth reviewing the key parts of a mesh, or the components of a mesh. So nodes, which are the red dots that you see here, these are the primary computational points, right, of your model. They are singular points in space. Nodes in the model will be connected by one-dimensional lines, these segments. Oftentimes, nodes will be used to define boundary conditions. Segments can also be used to define boundary conditions. And depending on the type of model domain that you're working with, for example, a channel. Channels in HGS are one-dimensional hydraulic structures, and those are mapped onto segments themselves. So being able to select segments becomes important when it comes to defining channels in your model. You then have two-dimensional faces, which are bounded at the corners by nodes and at the edges by one-dimensional segments. Again, 2D faces, they can be potentially selected or important when defining boundary conditions, for example, a rain boundary. But they can also be instrumental in defining certain property zones as well. So, for example, the overland flow domain is actually comprised entirely of two-dimensional faces, as well as the fracture domain. The fracture domain is basically going to be defined on faces throughout the interior of the model mesh. Finally, you'll have three-dimensional elements, and these are bounded at the sides by faces, at the edges by segments, and at the corners by nodes. Elements are going to be used to define porous medium property zones. You're not really ever going to define boundary conditions on elements themselves. But yeah, every mesh component is going to be instrumental in different parts of your model construction. It's also worth noting the verticality aspect. So node sheets are basically laterally connected, all of the laterally connected nodes, and then layers are all of the laterally connected elements. So some commands, if I go back to the HydroGeoSphere reference manual, for example, this command, let's say this command right here, clear chosen elements by SHP. This uses a shapefile, so you have to provide a shapefile, but then you also, the shapefile defines the sort of extent of the selection in the X and the Y dimensions. You would also need to provide the bottom and top layer numbers to help inform the vertical extent of that selection. So oftentimes commands will require you to name layer numbers or node sheet numbers. And layers and node sheets, they always start at the bottom with node sheet 1 and then increase in elevation. So in this case, the top node sheet is node sheet 5, and there's 4 layers in this model, layer 1 being at the bottom and layer 4 being at the top. So section 2.4 of the reference manual, it's worth scrolling through and highlighting some key commands that you think might be helpful to you. Some examples here: choose nodes based on a block, where you provide the coordinate range, top boundary, using planes, using, you can choose all of the nodes on the top or all of the nodes on the bottom, etc., etc. Okay, now we're going to talk about defining material properties. And earlier I made the comment that when I talk about model domain, what I really mean is a series of nodes that have a distinct set of governing equations. So in HGS, we support the porous medium or the subsurface domain, the surface domain or the overland flow. These are kind of interchangeable terms. We also support a dual continuum, so a dual permeability or dual porosity formulation. So in some cases, if you're using that, it's not done very, very frequently, but there is a dual domain. There's also a fracture domain, channel domain, well domain, tile domain, and evapotranspiration domain. Each of these domains has its own particular sort of shorthand. So PM for porous medium, OLF for overland flow, FRAC for fractures, CHAN for channels. And these little short forms, right, these become important when it comes to understanding some of the outputs that are being generated. So the binary output files, for example, will indicate which domain individual outputs are related to. In order to activate a domain, you basically just have to parameterize it somewhere in the model. And what that means is, by default, as soon as the grid is generated, it's assumed that the porous medium domain is active. It's not assumed that the surface flow domain is active. So to activate it, what you would need to do is just do something along the lines of choose node's top and then create a zone based on that selection, and then assign some overland flow properties to that zone. You can also use this command here, which is a little newer, called initialize domain. And basically this will take the current set of chosen elements, faces, or segments, depending on the domain, and it will put them all into zone number 1 and set it to have default properties. That by doing that, it has activated the domain. There's no command in HGS to say do fracture flow, for example. There's a command that we mentioned earlier, do transport, that is used to, the user will actively tell HydroGeoSphere that transport shall be run. It doesn't work that way with the individual model domains. But you can use this initialize domain type, or this initialize domain command rather, to sort of do a shortcut in activating these different domains. But you would then need to come through and overwrite those default parameter values with, the parameter values that are appropriate to your model in the context of your model. So I wanted to do this overview quickly just because the next thing we're going to be talking about is activating these domains and defining material property types. Now, typically in HydroGeoSphere model is going to include surface and subsurface. And this means you need to, before you even begin modeling, you need to start collecting data and trying to build a conceptual model to understand the distribution of geologic, hydrostratigraphic units and superficial soils in your model region, land cover classification data, and then climatology is going to be related to boundary conditions. But in the context of parameters, a detailed mapping out of the different hydrostratigraphic units and soils in the region, and land use classifications for the surface flow domain. The overall process of defining material properties requires, this is the recommended approach. You can do things a little bit more in a more complex way, but I'm not even going to bother mentioning it beyond that. I'm just going to recommend that you take the approach of defining material zones and use what we call material property files. So again, we have all these different domains, and so we support all these different material property files. The M props file for porous media, O props for overland flow, D for dual continuum, F props for fractures, W, T, C, and ET for wells, tile drains, channels, and evapotranspiration, respectively. Now, so the idea with these files is that they will contain named materials and all of their associated properties. The actual functional way of defining the materials themselves is then done by first making sure you're manipulating the right domain type using this command, use domain type. You will then tell grok, you'll tell HGS the name of the property file for the active model domain. This only has to be done once within a grok file. Then you'll select a property zone and then choose a material that's listed in the property file to map those associated parameters and property values onto the selected zone. So the easiest way to parse through how this works is to just look at a real world example, or to look at the example of the tutorial here. And again, I'll just highlight that, the comments are all here. So if this doesn't make sense later on, you can also just read through this line by line and it should hopefully clarify things. So first things first, we want to make sure that we're manipulating the correct domain type, and we're going to start with the porous medium. So we actively want to do this all the time. You use domain type porous media. You don't want to accidentally be working on a different model domain. So this is just good practice to invoke this command semi-regularly within your grok file. We then tell the model, or we tell HydroGeoSphere, that our property file is called r5.mprops. So let's take a look at that file. If we open it up, what we see is it works as an extension to a grok file, so you can always include comments in here as well. Then we have this word medium sand, this line medium sand, and this is a user-defined word. HydroGeoSphere doesn't really know what a medium sand is, other than the fact that there is an entry in this file called medium sand, and this is a user-defined thing. You could call it, depending on the project that you're working on, you could call it whatever you like, silty sand. It could just be some random designator, DK042, and then you could have DK041 and 043. It's entirely up to the user to name the materials associated with their project. Once, if we scroll further all the way down past these numbers, we see that there's an end. So this is basically all like a command block in a sense, and this becomes a custom command for this particular project. And it's telling, what we're basically doing here is we're saying that a medium sand has a hydraulic conductivity of 1.0 e to the negative 5 meters per second in this case. The units, just an aside, the units that you define in your grok file here, all of the inputs to your HGS model must be defined in these units. So this would, the hydraulic conductivity here would be in meters per second. Anyways, this soil medium sand also has a porosity of 0.34, specific storage of 1.2 e to the negative 7. And then we get into defining our unsaturated flow tables. So with a variably saturated flow model, you have to build some relation between saturation and relative hydraulic conductivity. And in this case, we're using a table of values. So this basically says at a saturation of 18%, our hydraulic conductivity is going to be 4.45 e to the negative 4 multiplied by this being our saturated hydraulic conductivity. And then if we scroll further down, we can see that the saturation relationship goes all the way up to full saturation, at which point the relative hydraulic conductivity becomes 1 times the saturated hydraulic conductivity. And we then end that table, and we also have to define a relationship between pressure head and soil saturation. So this is basically saying at a pressure head of -5, we have a saturation of 18%. And we then define pressure head relationship all the way to a pressure head of 0. In other words, this would be saturated soil and a saturation of 1.0. So this three-way relationship defines how hydraulic conductivity changes in the unsaturated zone just above the water table. We end the tables, we end the material, and this medium sand becomes a recognized thing that you can use to define the materials in your model itself. So just going back here, we've defined our properties file. And now what we're doing is we have to define our zone distribution of property zones as well. In this case, we're using a raster file. So basically it's just a gridded data file showing, in this case, there's going to be 2 zones in this file, zone 1 and zone 2. And these zones are associated with a medium sand and a coarse sand. So define the distribution of zones. We clear chosen zones. By the way, clearing things is also very important. Grok or HydroGeoSphere will keep your last selection in memory. So as you're going through building your Grok files, it's best practice to repeatedly and consistently clear things before you're going to select things. So we clear our chosen zone, we choose zone 1, and then we read the properties medium sand. So medium sand, pardon me, medium sand, which is a named material in our material properties file, becomes a sort of de facto command that we can reference in our Grok file. And we're just going to do the same thing for zone 2, which is a coarse sand. And then as you're defining things, you can always overwrite your properties and your zones with new stuff. So we talked earlier about how there's a clay lens. So right now, the elements that make up the clay lens or the location of the clay lens are either assigned to zone 1 or zone 2 and have the properties of medium sand or a coarse sand. What we're doing here is we're choosing elements using an AlgoMesh output file or an eChoose file. So just as a quick aside, in AlgoMesh, you can use the interface to point and click at a group of nodes and then save those as an nChoose file or a chosen nodes file. You can do the same thing with elements. When you do that, you would have to define the node sheet numbers, the range, the vertical range, as I mentioned earlier. So that's what's happening here. But basically, these lines are selecting the elements associated with that clay lens, and then it's overwriting their zone number and assigning them to zone 3. We then choose zone 3 and then read the properties of a clay, which if we scroll down, we have up here our medium sand, down here our coarse sand, and if we scroll all the way down, here to the bottom, we also have material number 3, clay. What I also want to point out here is that rather than defining your unsaturated flow properties using tabular relationships, in HydroGeoSphere, we also support the Brooks-Corey function and or the Van Gunukten functions. So in that case, you would use these commands, unsaturated Brooks-Corey functions, and then you would have to define the parameters associated with the Brooks-Corey function itself. This function basically then defines that 3-way relationship between pressure head, saturation, and relative hydraulic conductivity. So this file, the mprops file, is also worth reading through. There's plenty of comments in here about how this all works. But yeah, I'll just leave it at that for now, just to say that you can use tabular functions, tabular relationships between pressure head, saturation, and relative K, or you can use the Brooks, Corey, or Van Genuchten functions. Long story short, we've defined 2 and now 3 material property zones for the subsurface, including a medium sand, a coarse sand, and a clay. We now have to move on, and if we want to activate the surface flow domain, we need to define the properties. So it just follows the same pattern. Use domain type surface, define the property file for the active domain. In this case, it's the OPROPS file, and we can open that up and we can see that depending on the governing equations, of course, the properties are going to be different. So here we have to, for the surface flow, we define an X and a Y friction coefficient. These are Manning's friction coefficients. We can also define a real storage height. This basically determines that, or says that until the surface water depth is greater than 1 centimeter, water will not flow. It would be considered to be trapped under, like in a rill. A coupling length here, this is related to the exchange term and how water is actually dynamically exchanged between the surface and subsurface. I mentioned earlier how when you use the dual domain formulation, that your 2 meshes will be divided by, or they will be separated by some virtual distance. That virtual distance is defined by this coupling length value. In this model, we have a grassland and a ranch road land use classification zones. So that's the properties in our property file. We then, in this case, we're choosing all of the faces on the top of the model and calling it zone 1 and reading the properties of the grassland. And then we're overwriting the properties for some region here associated with the ranch road. And so we'll take a look at that in a moment. But anyways, yeah, so we then, we overwrite the zone number and then we read the properties of the ranch road. So we'll see the distribution of properties a little bit later on. We'll leave it at that for now. With respect to defining material properties zones, that's basically the recommended pattern. Is you define a zone, you define the materials themselves in your material property file, you define the distribution of zones, select a zone, read a material from that material property file, and then just carry on until all the material zones have been defined. A couple of other examples about how this would look, but I don't think we need to look at more examples necessarily, just in the interest of time. What I will point out is that every material property file, of course, is going to have different commands associated with it. Materials like porous medium, you're going to have to define hydraulic conductivity, specific storage, porosity, those unsaturated flow relationships. In the overland flow, it's friction coefficients, rill and obstruction heights, max flow depths. For evapotranspiration, it's things like canopy and interception storage, transpiration parameters, root depth, evaporation depth. It all really depends on the governing equation. In the reference manual itself, we have a subsection called materials and material properties, and it basically defines on a governing equation basis what those material definitions or property definitions are. So for saturated subsurface flow in the porous medium, for example, if we scroll through, it tells us what our default values are, and then you have all these commands that allow you to define actual properties themselves. K-isotropic is one that we just saw. This indicates where this command can be used. K-isotropic can actually be used directly in the grok file. It's not really recommended. We recommend, again, having named materials. That just keeps things a lot cleaner. But you could also just say, choose all elements in layer 1, and then assign K-isotropic directly to those elements. And you can sidestep the whole zone approach and the material property file approach. But I wouldn't really recommend that. It just gets a little messy. But depending on the section here, right, it's all delineated based on the governing equations themselves. If we go to, let's say, the surface flow section, we see that we have X friction, Y friction, time varying friction, time varying scaling of friction, real storage height, obstruction storage height, and again, it lists the scope here. We can do these directly in the grok file, or we can use them in the oprops file. If we were to go to the tile drain section, we can see that the associated commands can be defined in, this looks like it might actually be a typo. This might belong, this should be a tprops, I think. I'm going to have to just take a quick snapshot of that and make sure that I let our team know to update that. Anyhow, yeah, so all of the material properties themselves are listed throughout section 2.8 of the reference manual. Are there any questions on that whole process? Because that also is sort of can be sort of a tricky or complex sort of part to the workflow. Open to questions as we go through. So next up, we have initial conditions. Typically, it's pretty easy to define initial conditions. You would usually just use one command to define the initial conditions for each active model domain. You do need to define them for all model domains. So if you have a surface and a subsurface integrated model, you have to define an initial head in the subsurface as well as an initial water depth in the surface. There's a pretty standard set of commands that can be used. Initial head allows you to define a uniform value. Initial head surface elevation would allow you to define the initial head distribution just based on the surface elevation of the model, basically saying that the model is fully saturated to start. This one's really important as well. Initial head from output file. It allows the simulation to be restarted with the output from a previous simulation. So in HydroGeoSphere, it's really important to set initial conditions that are realistic, and that can be hard to do in the first iterations of your model. So what we typically recommend people to do is to run through a model spin-up process, and what we mean by that is you build an initial version of your model, define the initial condition to be fully saturated, for example, with this command here, and then run the model for a really long time just using average hydroclimatological forcing data. So the average net precipitation for a watershed, for example. You just let it run, basically indefinitely, until the water balance evens out and the whole thing kind of reaches a quasi-equilibrium state. So you just monitor the water balance file as it runs. And once the storage changes in each model domain kind of even out and get close to being zero, then you just manually terminate the model run and use the results from that simulation as the starting point for subsequent transient simulations. So the reason that that's really important is because, you know, if you just start your model from an arbitrary distribution of heads, maybe you say, hey, my initial head is going to be based on a water table depth of 15 meters. You may have a pumping well somewhere in your model that then is trying to pump from a dry soil, which it can't do. That's not physically possible. So starting with just starting a transient simulation where things are going to change over time from an arbitrary initial condition is just numerically very, very difficult for HydroGeoSphere to do. And so we really do highly recommend that people familiarize themselves with this sort of spin-up procedure. And so usually when I get to this point in my presentation, I like to again remind people that we have a YouTube channel with a ton of additional materials and training stuff. There is one particular video that I'll highlight. It is model convergence and optimizing runtimes with HydroGeoSphere. I'll drop a link to this in the chat just for convenience. This lecture is an hour and 15 minutes, and optimizing runtimes with HydroGeoSphere is something that every new user really struggles with. So this lecture really is focused on how to get people off to the right start and not get stuck with a model that fails to converge. And it talks in detail about this whole model spin-up procedure, right? So in this section of the tutorial, I start talking about steady state versus transient flow and the importance of a meaningful initial condition and how you can use outputs from one model as the starting point for subsequent model runs. So not to pile on another hour of training, but I do highly recommend this video if you're going to be continuing your research with HydroGeoSphere. I think spending an hour and a half watching this will save you more than an hour and a half down the line. So defining initial conditions, yeah, it's generally pretty simple. You're going to use one command to define the initial conditions across the full model domain. In our particular example model here, we are not doing really the recommended thing. We are just using some arbitrary initial head depth to water table. It's basically just saying the water table is 1 meter below ground surface, and in the surface domain we have a water depth of about 1 millimeter. When it comes to the surface domain, oftentimes people will they'll want to just set an initial water depth of 0. We recommend setting it to something slightly larger than 0, just because zeros can be numerically tricky for HGS to actually handle. So setting it to something infinitesimally small is going to be a lot easier for HGS to handle than an actual 0. Okay, 30 minutes left. We're going to keep moving right along here. Next up is boundary conditions. So again, very important aspect of building a conceptual model is knowing where the water comes from and where it's supposed to go in your HGS model. And this is done using boundary conditions. They're mathematical forcing functions that force water into or force water out of or allow water out of the model. When you're defining boundary conditions in HydroGeoSphere, you will first need to create a set, either a node set, a face set, or a segment set. Individual boundary conditions are applied to different mesh components, either nodes, faces, or segments. And node sets, face sets, or segment sets are simply selections of nodes, can be one node or many nodes, that are saved and given a name. If you want to apply a boundary condition and you're not exactly sure which type, which mesh component it should be applied to, you go to the boundary conditions section or subsection of the manual. Under type, we have basically all of the different boundary condition. We've got flow boundary condition types, which basically give you the full range of specified heads, specified fluxes, fluid transfer, free drainage. If we go to, let's say, specified fluxes, every boundary condition is going to include a little example snippet from a grok file, and it tells you right in there. This is the easiest way of just cutting through the nonsense and understanding what type of set is applied for a particular boundary condition. So fluxes are applied to faces. And this is a flux that's defined as an input flux in length over time. So let's say meters per second, or you could convert a millimeters per hour rainfall rate into meters per second. And that would then be converted to a nodal volumetric flow rate by multiplying by the contributing area of a chosen face. So there's also the rain boundary condition. Then you get to flux nodal. So this is where you're defining specifically a nodal volumetric flow rate, and it's applied directly to nodes, either one node or many nodes, but via the concept of a node, a predefined node set. So that has to be done. You have to create your set before you define your boundary conditions. And then to define the actual boundary condition, you're going to see an input sort of style like this. You use the boundary condition command, which is a block, so it has to be ended later on. You'll then define the type using the type command. The types themselves are then things like flux nodal. So boundary condition type flux nodal. Then you would define a node, face, or segment set. In this case, the node set top would have been predefined elsewhere in your grok file. Then you'll define a time value table, a time raster table, or a time file table. So some boundary conditions don't require you to necessarily define anything. For example, a critical depth boundary condition, these are often applied in the surface domain. They simply allow any water pooling along those segments to flow out of the model. So we typically apply those right around the outer edge of the model. So all the water flows, towards the lowest point in the model basically, and intersects with a critical depth boundary condition and simply leaves. So that's an example where you don't actually have to define any value, But more often than not, for example, with a flux nodal boundary condition, you would have to define a time and a value. In this case, it's done using a time file table, and this input file here would contain a list of nodes and actual flux values. We have a simpler example here in the tutorial. So I mentioned already critical depths. These don't require a time value table or anything like that. You just define the type. The name is optional, but it would be incorporated into the output file names and into your water balance file, for example. Now we define our segment set outlet, which again has been previously defined up here. And we also have this optional command TecPlot output. I recommend including this with every boundary condition. It will just generate a specific output file for that boundary condition, which can be handy to have later on, although it's not always necessary. It's just good practice. So we're defining a second critical depth boundary condition here. And now we're getting to an example, a rain boundary condition that does include a time value table. So this is basically just saying, okay, well, at time 0, we're going to apply a flux of 5.55 e to the negative 7 meters per second, which is equivalent to 0.2 centimeters per hour. And given that we haven't included a second time, that flux will just be maintained for the full duration of the simulation. Again, we have this TecPlot output. It's optional, but good to have. Now we get into our porous medium boundary conditions. So first we're going to be applying a flux nodal boundary condition with a time varying input. And this is basically, a flux nodal is used to typically represent pumping wells. So we have an output file that was generated in AlgoMesh. It's used to select a couple of nodes. I'll just very quickly open up the tutorial just to give you a sense as to the sort of spatial distribution. Okay, so in this image here, we have this node here, another one down here, and right here. These represent the locations of the pumping wells. So in this tutorial, if you follow along, at one point or another, you're instructed to click, 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 and click all 4 of those, and then to save them as an nChoz file. And that's what's being referenced here. And we're then saying they're located in node sheet 2. We create the node set wells. We then define the boundary condition type as flux nodal, apply the node set wells. We, in this case, didn't apply a name for this boundary condition, but that can always be done. That would just be done using the name command, so we could just add that in now. And now we have a time value table with actual time varying values. So starting at t equals 0, we apply a negative flux, and this indicates that we're removing water from the model. And this value of 0.00002777778 is basically negative. It's 100 liters an hour. So, and that's cycled on and off every 21,600 seconds or every 6 hours over a 24-hour period. That's basically it for boundary conditions. I mean, they all follow this same pattern. The only real trick is to know what type of boundary condition requires what type of set, whether it's a node face or a segment set. Also, if you have a raster file, let's say your precipitation boundary condition is being applied over a large enough area that you actually have to apply or define distributed or spatially distributed precipitation, you can use a time raster table instead. And instead of applying a single value, what you would then do is just point to, my ./input data folder, rain day 1, right? Whatever your raster file extension is. So it's possible to apply both spatially and varying boundary condition values. We then get into evapotranspiration boundary condition and properties. So something important to note with respect to evapotranspiration is that you need to apply it as both a property zone, or rather an actual model domain with all of its associated properties. But you also need to apply a potential evapotranspiration boundary condition. If that isn't done, then ET will not really, it won't actually do anything in your model. So we start with the boundary condition. So the ET boundary condition is applied to the surface. So this can be a little bit confusing because we do have an ET domain, but the ET domain always coincides with the surface of the model. So the boundary condition itself is applied to the surface. We name the type, we provide a name, provide a face set. Now in this case, the face set had already been created up here when we were defining the rain. Spatially, they both coincide in the same location, and so we don't need to create a second face set for this boundary condition. And again, we have a time value table, just a consistent PET rate. We then apply PET properties. Thanks for coming, David. Just reach out anytime if you have any questions. Have a good day. Yeah, so ET properties, they're going to have their own ET properties file. So we can quickly open that up and take a look. It will contain, in this case, we just have one zone called ET1. And you can see we have an evaporation depth, a root depth. We've defined how root and evaporation rates decay over depth. So in this case, quadratic. Leaf area index tables, transpiration fitting parameters, transpiration limiting pressure heads, and basically just all of the parameters associated with the 1978 paper Christensen and Jensen. Again, it's referenced in our theory manual, so you can look into that, that governing equation. You choose a zone. In this case, it's going to be applied spatially homogeneously across the top, so just zone 1. Choose, your chosen zone, read the properties, and you're good to go. Now, when it comes to evapotranspiration, PET represents the upper limit on evapotranspiration rates. The actual evapotranspiration rate will be determined based on the governing equation itself and the availability of water in the evaporation zone. So based on the root and evaporation depth that you've defined. If the actual evapotranspiration rate is less than the defined PET, then the actual evapotranspiration rate is applied to the applicable portions of the mesh. However, if the actual evapotranspiration rate exceeds the PET rate that you've defined as a boundary condition, then the PET rate is applied. Again, it's just, this defines the upper limit of potential evapotranspiration. Okie doke, and now that's boundary conditions. We now are on to the last two small sections, numerical and time settings, and then model outputs. So we've already talked a little bit about how to review the outputs of your model. So we don't have to go over that in much detail again. What I will say is just reiterate that becoming a good HGS modeler does require you to be able to sort of read and understand this output, understand in a general sense the behavior of the model, and then to select the correct type of numerical runtime settings to optimize model runtimes. So we've talked already about how all of the different control settings work. So yeah, time step control. Generally, you're going to want to use the adaptive time stepping approach rather than fixed time steps. So there's general time step settings such as initial time, the initial time step size, maximum time step size, maximum time step multiplier. There's also a really important command called output times. This output times command, if I scroll a little further down, this defines not only periods of time where a snapshot of model results will be taken, this is when your binary output files are generated, but it also defines the overall simulation duration, right? So the total length, total duration of the model. In this case, it'll be 24 hours. But then for general, for general time step settings, again, minimum and maximum time step multipliers, initial time step size, you can define a minimum time step size as well, maximum time step size. You then have to define numerical solution criteria. Oh, right, sorry. Before the time steps, just again to reiterate these control variables and how adaptive time stepping works. This is outlined in Appendix, I believe it's Appendix C of the reference manual. Runtime time step output. So this section defines in more detail all of the individual variables listed in the runtime output. And then it also describes towards the bottom how the actual adaptive time stepping works in greater detail. But I already explained that earlier. Just suffice it to say that in your grok file, you'll want to define some general time step controls as well as the adaptive time stepping controls. Then there is the actual numerical simulation criteria themselves. So the most important ones being the Newton absolute and residual convergence criteria. There's other commands as well, flow solver maximum iterations, compute under relaxation factor. Don't need to dig into these too much today. But if you ever find yourself really struggling with model runtimes, again, we talk about these in more depth in that tutorial that I mentioned, or that training session that I mentioned on our YouTube channel. Then we get to output control. So this is usually the last part of a grok file. Output control, we define our output times. Well, we can also define a whole bunch of commands that will produce more detailed, refined model outputs at particular points of interest. Things like observation points, where we basically just define, the XYZ coordinates. It will flag the nearest node, and it will start to track more detailed output at that individual node at every single time step, as opposed to only at output times that were defined using this command up here. We can also do things like create fences of nodes to create hydrographs. So if you know that there's a location with a stream, you just choose 3 nodes that kind of branch across that stream, and you can then create hydrographs at that location. We can also choose particular elements, or like zones or elements, for fluid volume tracking, so we can get a more detailed look at, basically the mass balance and movement of water into and out of that zone. We also, in this grok file, in this tutorial file, we have a section on particle tracing as well. It's currently skipped because it increases the model runtimes a little bit, but this is something that you can also look into yourself, when you're reviewing the tutorial. That brings us to the end of the grok file, right? So just to recap, we write the grok file that contains all of our information about the input, or the definition of the model itself. We then prepare the actual simulation by running grok.exe. That is the preprocessor that reads the grok file, sets up the matrix of equations. phgs.exe then runs the actual numerical simulation. And then finally, hsplot or hgs to VTU will take those, the binary model outputs, and reformat them for a visualization product. That brings us to the end of the training session, at least here in the context of our presentation slides. But before we go, what I will do is run this model and highlight a few key things. So something that we haven't really talked about yet is just kind of troubleshooting. So now that we've reviewed the whole grok file, we can run the whole grok file. Earlier when we ran it, we had included a skip command, which I'm just going to make sure to remove. So there's skip on, skip rest commands, which allow you to turn on, like activate or deactivate huge chunks of the grok file. So I'll make sure to remove that. If I ever make a change, of course, it's important to save the file, and then we will run grok again. And we're going to immediately run into a couple of errors or problems. These are added into the tutorial on purpose to try and illustrate to people and show you what happens when things don't go right, which invariably will happen. So first of all, I talked earlier about warnings and errors. If you see something like this, it's a fatal error. It's halting the execution of grok. In this case, it's an easy fix. It's an unrecognized boundary condition type. I put a typo into this boundary condition on purpose. So we'll go fix that. It's the potential evapotranspiration boundary condition. You'll just have to change this O to an I. And of course, if we make a change, we have to save the file. And then we can run grok again, and it should be able to get past that error. So in this case, normal exit, no warnings or anything. We're now ready to proceed to actually running the simulation. Again, just to point out, a whole bunch of additional output files have been generated here. We'll run phgs. So now we're running into a new problem. It may look like it's making progress, but as you continue to use HydroGeoSphere, you will eventually start to recognize this type of behavior. What's happening is that the numerical, the Newton iterative solver is running through the maximum number of available iterations. So in our inputs here, we've said that we have 12, maximum of 12 iterations. And if HGS isn't able to solve the system of equations for this time step in 12 iterations, what it does is it cuts the current time step in half and tries again. But sometimes it just kind of gets stuck in this loop. What ends up happening at the end of the day, if you let it go and go and go, your time step size starts to become infinitesimally small. Eventually, it will get so small that HGS will just crash entirely, which is what's happening here. Current time step cut in half, redo time step. Oops, sorry, your current time step is less than the minimum allowed time step. So this is a common problem. It has many potential causes. You may have created a system of boundary conditions that is sort of impossible. Maybe a pumping well trying to remove water from a dry zone. That can't be done. It's not physically possible, and therefore HGS will just kind of spin its wheels before eventually crashing. Or you may have created, maybe you've got a model mesh that has really poor quality mesh elements. You know, if you maybe have a triangle somewhere in your mesh that is infinitely thin, it can be hard to overlook because it just looks like a line when you're looking at your mesh. That's why it's important to maintain high mesh quality, but that could be another reason why your model fails to converge, is basically the structure of the mesh is not amenable to a solution. Maybe you've accidentally included some material property that is impossible. Maybe you accidentally put in a porosity that is a few orders of magnitude out of range, or hydraulic conductivity that, you know, maybe a unit conversion blunder. So there's a lot of reasons why this can happen. In this case, it's an easy fix. It's because we applied convergence criteria that are extremely, extremely tight. The simple fix here is to just change one of these 10s to maybe a 3 or a 2. So this basically says, you know, if these were each to the -10, that's basically trying to thread the needle. You need your solution to be extremely, extremely, extremely accurate. This basically gives HGS a wider goal to work with. So if we make any changes, of course, we need to always save our project, and then we would run grok again, and then we would run phgs. I'm just going to press Control-C here, which crashes the simulation. I'm doing this on purpose because I want to demonstrate one other thing. There is a really handy feature that we have called the debug control file. So I'm putting these back to be very, very tight, and I'm going to save the file. And before I'm going to run the model, I'm going to open the debug.control. So at every iteration of the Newton solver and at every time step, HGS checks this file, and what it first sees is this command debug off, which tells it to ignore the rest of the file. If you add a comment here, then it will start reading through each line. Now each line by default here has an exclamation point, and so it's ignored. It's treated as a comment. But if you run your model with extremely, maybe you need to change the model convergence criteria on the fly. Maybe your model ran for a day and it got up to simulation time of like 120 years, but then some boundary condition turns on and it's struggling to converge on a solution. You don't want to restart your model from t=0 because you will have lost a day at that point. What you can do instead is, while it's struggling, you can actually just open up this debug control file and you can modify numerical simulation criteria on the fly. So we can change these to 2s, save this file, and as soon as we do that, we can see that it starts to solve every time step much faster, and it actually starts moving forward in time. So this is a really, really handy feature. Again, for an advanced user, it's kind of indispensable. It just allows you to fine-tune things while the model is running. This model itself shouldn't take too long to run. It's already at 60–70% finished. So we'll just let it run for another moment here, and we will very quickly run HGS to VTU, hit enter. As we're going through here again, we have all these binary output files, but this model also includes a number of observation points. So we can see these observation point output files. These are just time series output files, so you can easily, load them into Excel or whatever you like to visualize the results. Same thing with our hydrograph output. It's a simple time series file. It contains, basically, first column is time, and then you have surface flow rate, porous media flow rate, and total flow rate through that hydrograph. You've got your water balance, of course. But let's just load these results into ParaView, and we can just very quickly see what we've been working with this whole time. So we load this in here, we turn this on. Here's our model. We can see now the distribution of actual elements there. What we're looking at right now is the elevation to groundwater table, but we'll change that to, let's say, saturations. And right now, initially, because we used an arbitrary initial condition, the model is just mostly saturated except for at the surface. As we step forward through time, we can start to see a more realistic distribution of saturations forming. So this is the lowland area. As we run this model over a 24-hour period of rainfall, just bit by bit, water starts to essentially accumulate here at the lower area. I have to say, though, this tutorial is not really representative of a real-world model. The boundary condition data and everything that we have put into this model is more designed to be to have the model run quickly. It's here just as a learning tool, really. It's up to you as professional water resources engineers to, of course, put more realistic information into your own models. But that brings us to the end of the training session here. I see another question in the chat, so I'll address that. And if anybody else has any questions, happy to answer them now. Also happy to answer any questions you may have by email as you work through this tutorial. Again, I recommend working through this comprehensive tutorial as sort of your next step as you learn about HydroGeoSphere. So the question is, how about the resolution of the model? For instance, can you distinguish 5-meter elements at catchment scale? That is a tough question to answer with. You can't just say yes or no. It really depends on the power of your computer, how much time you're willing to allocate to model runs. A model like this is actually quite small. I mean, I'm not 100% sure, but I think it's like maybe it's probably like a few dozen square kilometers at most. So these mesh elements are also quite small, but at catchment scale, what does that really even mean? Some catchments are 2,000 square kilometers. Other catchments are, 50,000 square kilometers. What I will say is this: as your model size grows, you are still going to be limited by the computational capacity of your workstation. As I mentioned earlier, as a new user, I recommend that you try to limit yourself to 1 million nodes max, far lower if you can, and to take a really staged, step-by-step approach. First, build yourself a really coarse model, and once you have it well calibrated, you can then create a new version of the model that is more refined, that has higher mesh resolution. Going through the process of calibrating a coarse model and then mapping out what you've learned from that coarse model onto a refined model will probably save you a lot of time, because let's say a coarse model takes an hour to run and the refined model takes 10 hours to run. If you need to calibrate your model by running it 12 times, you can run that coarse model 12 times easily in a day. Whereas with a refined mesh that might take 10 hours at the baseline to run, well, that calibration process is going to take a lot longer. So you can distinguish, you can have a 5-meter resolution for a catchment scale model. You can have a 5-centimeter resolution for a catchment scale model. But those two models are going to take very different times to run through a simulation. So it's impossible to really answer that question clearly. All I can say is that the resolution of the model is entirely up to you, but there is obviously going to be an upper limit on what you can. There's going to be a limit on what you can do, just based on, the computational resources that you have available to you. The other thing that I'll mention is that this particular model that we've run, again, it's only run over a 24-hour period. Most of the time, people will want to run models for years or decades. That is obviously going to also significantly increase the model runtime. So, yeah, it's an impossible question to answer directly. There's too many variables to account for. Ultimately, the mesh resolution is entirely up to you, but you'll have to figure out a way to balance the needs of, the practical needs of being able to run a model in a reasonable amount of time with your desire to have ever finer mesh resolution. So the follow-up question is, should I start modeling for a small area? Not necessarily. It doesn't necessarily have to be a small area. Like, even if I open this up again, let's say that this is 100 square kilometers. You can build a model of this 100 square kilometer area that has 50,000 nodes, or you could build a version of this model of 100 square kilometers that has 1,000,000 nodes. The 1,000,000 node version is going to take a lot longer to run. It's not necessarily about the size of the area itself. It's more so about the complexity of the model, which is more related to how many nodes and elements there are, how many governing equations are active. If you really want to dig into this question, again, I would highly recommend reviewing this video here. The slide that is currently loading here essentially talks about this very question. More domains and more processes, so more nodes, more exchange terms, more governing equations, those equal more unknowns, which equals longer run times. So it's not about the size of the model, it's about the number of nodes. That's the most important thing. Yeah, this question is explored in more detail right here in this particular video. So, yeah, I understand if you need to have 5-meter resolution in your model, then I'm sure you can find a way to do that. It just might mean potentially not modeling at the full watershed scale. We have some commands, for example, they're called regional model commands. I'm just going to pull up a couple of visual aids here. So we talked about model scale earlier. We have some commands. If you go to our reference manual and you look up regional model, so we have regional model commands. What this allows you to do is you could build, for example, a watershed scale model. Just going to create a new slide and do a little bit of a drawing. Pardon me. Okay, so let's say you have a watershed. This is your full watershed, and you're particularly interested in maybe there's a stream network. And this is let's say this is your outlet. Maybe you build yourself a watershed scale model, but you're really mostly interested in evaluating, hyporheic exchange or something on a stretch of the stream. So this can be, we'll call it L, and we'll call this larger one R. You can run a regional model and then use the results of this regional model to define boundary conditions around the edges of your local model, right? So this can be used to define things like the initial head distribution or time varying specified heads, for example. So you don't always have to work at the watershed scale, but you can still run a watershed scale regional model and use the outputs to define sort of the nature of inputs for a smaller local model. So this section of the manual describes how this is done. In your local model, you would just point to a regional model, and then you can map zones from that regional model. You can also map initial heads from a regional model output file. So initial heads, and then also hydraulic conductivities, as well as boundary conditions like, specified heads. So again, it's really hard to, at the end of the day, you will always need to balance competing interests. Those two competing interests being wanting to run the model quickly, but at the same time carry more model resolution, because the higher resolution you have, the more realistic your model outputs will be compared to the real world. But these two things, are going to tip the scale in one direction or the other. At the end of the day, it's a balancing act. Okay, if there's no other questions, again, I'm more than happy to answer any questions that may come up as you continue to explore HGS independently. My email is bmcneil with 2 L's at aquanty.com. I'm putting that in the chat right now. Happy to answer any questions that come up. Just reach out. There's no need for you to spend necessarily hours looking through the manuals, searching for an answer, when I may be able to answer a question you have in just a few minutes.